somewhere between Mars and Jupiter, drifting through the cold emptiness of interplanetary space. At an average temperature of negative 110 degrees Celsius, there is an ancient world that almost nobody has ever heard of. It is not a moon, it is not a comet. It was, for a brief and extraordinary period in human history, considered a planet. And then, like so many inconvenient truths in science, it was quietly reclassified, pushed to the margins, and forgotten. Its name is Pallas, and it is one of the strangest, most battered, and most important objects in the entire solar system. Pallas is roughly 512 kilometers across. That makes it wider than the entire country of Austria, measured from its northern border to its southern tip. If you could somehow lift this asteroid and drop it gently onto Western Europe, its shadow would stretch from Paris to the Swiss border. If you laid it across the state of Colorado, it would span from Denver to the Utah line. It is not small, it is not insignificant. It is, in fact, the third largest object in the asteroid belt, that vast ring of rocky debris orbiting the Sun between the fourth and fifth planets, a region of space containing millions upon millions of fragments, ranging from grains of sand to worlds hundreds of kilometers wide. And yet, despite its enormous size, despite its profound scientific importance, despite the fact that it has been silently orbiting the Sun for more than 4.5 billion years, faithfully completing lap after lap around our star, while continents drifted, species evolved, and civilizations rose and fell, on the small blue planet 300 million kilometers away. No spacecraft from Earth has ever visited Pallas. No probe has ever photographed its surface up close. No camera has ever captured the detail of its immense craters. No spectrometer has ever tasted the composition of its ancient dust. No seismometer has ever listened to the tremors deep inside its rocky body. Think about that for a moment. Humanity has sent spacecraft to comets, to dwarf planets, to moons of Saturn orbiting more than 1 billion kilometers away. We have landed on the surface of asteroids, physically touched them with collection arms, scooped up samples of their soil, and returned those samples to Earth. We have photographed Pluto in exquisite detail from a distance of more than 5 billion kilometers. And yet Pallas, this hulking, primordial relic from the birth of the solar system, a world large enough to qualify as a minor planet, remains almost entirely unexplored. There is a reason for that, and the reason is itself one of the most baffling mysteries in planetary science. Pallas does not orbit the Sun the way most objects in the asteroid belt do. Most asteroids travel around the Sun in relatively flat, well-behaved paths, staying close to the same orbital plane that all 8 major planets share. This plane is called the ecliptic, and it is one of the most fundamental features of the solar system's architecture. The ecliptic is not an arbitrary reference line. It is a physical consequence of how the solar system formed. When the cloud of gas and dust that birthed our star collapsed and flattened into a spinning disk, everything that formed within that disk inherited the same basic orientation. The planets orbit in this plane. Most asteroids orbit in this plane. The ecliptic is the solar system's floor, and nearly everything walks upon it. But not Pallas. Pallas tilts. Its orbit is inclined at roughly 34.8 degrees to the ecliptic, a wild, steep angle that sends it plunging above and below the plane of the planets like a ship cresting enormous invisible waves in an ocean of empty space. No other large body in the asteroid belt behaves like this. No other object this massive orbits at such an extreme angle. Ceres, the largest asteroid, orbits at an inclination of about 10.6 degrees. Vesta, the second most massive, sits at 7.1 degrees. These are already elevated compared to the planets, but they are modest, explainable, unremarkable. Pallas, at nearly 35 degrees, is in a category by itself, and to this day, despite decades of research and increasingly powerful computer simulations, no one can fully explain why. That tilt is not just a curiosity. It is not just an oddity to be filed away in a textbook. It is the reason Pallas has never been visited by a spacecraft. Reaching an object on such a sharply inclined orbit requires an extraordinary amount of energy, a massive expenditure of rocket fuel, just to climb out of the ecliptic plane and match the asteroid's trajectory as it swoops above and below the rest of the solar system. The technical term for this energy cost is delta V, the total change in velocity a spacecraft must achieve to reach its target. and the delta V required to rendezvous with Pallas is staggeringly high, higher than what is needed to reach many objects far more distant. It is cheaper, in terms of fuel and trajectory design, to send a spacecraft all the way to Jupiter, more than 700 million kilometers away, than it is to match the orbit of Pallas at less than half that distance. That single geometric fact has kept one of the largest remnants of the early solar system locked away from close investigation for the entire 67-year history of space exploration. But what makes Pallas truly strange goes far deeper than its orbit. Recent observations, gathered painstakingly from the most powerful telescopes on Earth and in orbit around it, have revealed that Pallas is covered in impact craters so severe, so numerous, and so violent that its surface resembles nothing else in the asteroid belt. It looks, according to the scientists who studied it, like a giant golf ball that has been pummeled by billions of years of catastrophic collisions. Its craters are roughly twice as numerous as those found on Vesta, another large asteroid that has been visited and mapped by NASA's Dawn spacecraft. And the reason, researchers now believe, is precisely that wild orbital tilt. Pallas does not travel gently through the asteroid belt. It does not glide smoothly along a well-worn path. It punches through the belt's midplane. Twice every orbit, it crosses the densely populated region where most asteroids congregate, and it does so at a steep angle and a terrifying relative velocity, smashing into smaller objects at average impact speeds of roughly 41,000 kilometers per hour. It is, in effect, the most battered large object in the inner solar system, and it has been enduring this punishment for longer than life has existed on Earth. There is something else, something that makes Pallas not just scientifically interesting, but cosmically important. Pallas is a protoplanet. It is not merely a leftover chunk of rock, not just a piece of debris from some ancient collision. It is a world that began the process of becoming a full planet and then stopped, frozen, interrupted, suspended in a state of incomplete becoming. It formed in the earliest days of the solar system, in the first few million years after the sun ignited, when the disk of gas and dust surrounding the young star was condensing into the worlds we know today. Pallas grew. It accumulated material. It began to heat up from the decay of radioactive elements within its body. It started to differentiate, separating into layers the way Earth did, with heavier elements sinking toward the center and lighter material rising to the surface. And then something stopped it. Something halted its growth before it could finish becoming a planet. Whatever that something was and why it happened is one of the most important unsolved questions in the study of how planets form. By the end of tonight, you are going to understand what Pallas is, why it orbits the way it does, what its battered surface tells us about the violence of the early solar system, and why this forgotten, neglected, impossibly strange world may hold the key to understanding how Earth itself came into existence. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand why Pallas matters, and why its existence represents one of the great unsolved puzzles of planetary science, we first need to understand where it lives. And to understand where it lives, we need to understand the single most important failure in the history of the solar system. Between the orbits of Mars and Jupiter, there is a gap. Not a small gap. Not a subtle thinning out of cosmic real estate. A yawning, enormous stretch of space where, by every reasonable expectation, by every physical principle that governs how planets form, there should be a planet. The distance from Mars's orbit to Jupiter's orbit is roughly 550 million kilometers. That is more than 3.5 times the distance from Earth to the Sun. In that vast expanse of orbital real estate, there is enough room, enough raw material, and enough gravitational potential for a world the size of Earth, or even larger, to have formed. The basic conditions are met. The ingredients are present. The physics allows it. But it did not happen. Instead of a planet, there is the asteroid belt, a ring of millions of rocky and metallic fragments, ranging in size from specks of dust to minor planets, all orbiting the Sun in a broad, diffuse band. The total mass of this entire belt Every rock, every pebble, every microscopic grain combined is less than 4% of the mass of Earth's moon. That is an extraordinarily small amount of material for such a vast region of space. It is like discovering an entire continent of land that contains nothing but a thin layer of gravel. Something should have grown here, something tried to grow here, and something prevented it. For centuries, the existence of this gap tormented astronomers. In the late 1700s, a mathematical pattern known as the Titius-Bode law seemed to predict the distances of the known planets from the Sun with uncanny, almost suspicious accuracy. This rule, first noted by Johann Daniel Titius in 1766 and later publicized by Johann Elert Bode in 1772, described a simple numerical sequence that, when applied correctly, produced distances remarkably close to the actual orbital positions of Mercury, Venus, Earth, Mars, Jupiter, and Saturn. The pattern was elegant, it was compelling, and it predicted a planet at a distance of roughly 2.8 astronomical units from the Sun, right in the middle of what we now call the asteroid belt. The prediction was so convincing that an organized search was launched. A group of astronomers, calling themselves the Celestial Police, divided the sky into zones and systematically scanned for the missing planet. They were convinced it was there, the mathematics demanded it, the pattern required it, and they were determined to find it. On the first night of the 19th century, January 1st, 1801, before the Celestial Police could complete their search, an Italian astronomer named Giuseppe Piazzi stumbled upon the answer by accident. Piazzi was not looking for a planet. He was working at his observatory in Palermo, on the island of Sicily, methodically compiling a star catalogue, recording the precise positions of thousands of faint stars, with the same diligence and patience that would characterize the best astronomical work for centuries to come. But on that night, the very first night of a new century, he noticed something that did not belong. A tiny point of light, almost too faint to measure, had moved slightly from the position it occupied the previous night. Stars do not move, not perceptibly, not from one night to the next. Planets do. Piazzi tracked the object for 41 consecutive nights before illness forced him to stop. He measured its position with painstaking care, night after night, and came to a staggering conclusion. He had found an object orbiting the Sun at almost exactly the distance predicted by the Titius-Bode law. It appeared to be the missing planet. The astronomical community was electrified, but there was a problem. Piazzi had lost the object. After his illness, the body had moved too close to the Sun's glare to be observed, and no one knew where it would reappear. This is where a young mathematician named Carl Friedrich Gauss, then just 23 years old, entered the story. Gauss developed an entirely new mathematical method for calculating orbits from a minimal number of observations, a technique so powerful that it is still used in orbital mechanics today, more than 2 centuries later. Using only Piazzi's 41 nights of data, Gauss predicted where the object would reappear in the sky after emerging from behind the Sun. He was right. The object was recovered exactly where Gauss said it would be. It was named Ceres, after the Roman goddess of agriculture, and it orbited the Sun at 2.77 astronomical units, remarkably close to the Titius-Bode prediction. The gap had been filled, the pattern was vindicated, the solar system appeared complete. For 15 months, this was the accepted story. Ceres was the missing planet. The mathematics had triumphed, the search was over, and then, on March 28, 1802, the entire narrative collapsed. On that night, a German physician and amateur astronomer named Heinrich Wilhelm Matthias Olbers was observing the sky from his home in Bremen. Olbers was not an ordinary amateur. He was brilliant, methodical, deeply knowledgeable about celestial mechanics, and possessed of the kind of patience that separates great observers from merely competent ones. He was tracking Ceres, following its orbit as the scientific community had been doing since its recovery based on Gauss's calculations. But on that particular March night, while scanning the constellation Virgo, he noticed a second object near Ceres that he had not seen before. It was faint, it was moving against the background stars, and it was at nearly the same distance from the Sun as Ceres. Olbers had found Pallas, and with its discovery, everything scientists thought they understood about the space between Mars and Jupiter was suddenly uncomfortably wrong. If Ceres was the missing planet, then what was Pallas? It could not be a moon of Ceres, because it was far too distant from it, and moving on a completely independent orbit. It could not be a comet, because it showed no tail, no coma, no fuzzy envelope of gas. It was, by every measurable criterion, a second body occupying the same region of space as the first. Two objects where there should have been one. Two worlds where the mathematics predicted a single planet. Olbers puzzled over this. He was troubled by it, and he eventually proposed an explanation that would dominate scientific thinking for the next 50 years. An explanation that was dramatic, intuitive, and ultimately incorrect. He suggested that Ceres and Pallas were not independent objects that had formed separately. Instead, they were fragments, debris, pieces of a single, larger planet that had once occupied the gap predicted by the Titius-Bode law, but had been destroyed, shattered by some catastrophic event, perhaps an internal explosion or a colossal collision with another body. This exploded planet hypothesis was elegant. It explained why there were two objects instead of one. It predicted that more fragments should be found, which they were. Juno was discovered in 1804 by Carl Ludwig Harding, and Vesta was found in 1807 by Olbers himself. Four objects, all orbiting in the same zone, all apparently consistent with the debris of a destroyed world. The idea captured the imagination of the scientific community. It was satisfying. It was complete. And it was wrong. It would take more than a century and a half of accumulated evidence, and a revolution in our understanding of how the solar system formed to understand the truth. There was never a planet between Mars and Jupiter. There was never a single large world that shattered into pieces. Instead, there was a planet that was never born, a world that was strangled in its cradle by the gravitational tyranny of the largest planet in the solar system. Jupiter. Jupiter is, without exaggeration, the most important object in the solar system after the Sun. It contains more mass than all the other planets combined, more than 300 times the mass of Earth, and its gravitational influence extends far beyond its own enormous orbit. Jupiter is not merely a planet. It is an architect, a sculptor, a destroyer. It has shaped the trajectories of comets, cleared resonance gaps in the asteroid belt, influenced the orbits of every inner planet, and quite possibly determined whether or not life could ever have arisen on Earth. And in the earliest days of the solar system, when the protoplanetary disk was still thick with gas and dust, and the planets were still coalescing from swirling clouds of debris, Jupiter's gravity reached into the region between Mars and its own orbit and stirred the raw material so violently, so thoroughly, and so relentlessly that the building blocks of a planet could never come together. Imagine the process of planet formation as a construction project. In most parts of the early solar system, small rocky bodies called planetesimals, objects ranging from a few meters to a few tens of kilometers in size, were colliding with each other at low speeds, gently merging, slowly growing, gradually building up larger and larger objects through a process called accretion. The impacts were soft enough that the colliding bodies stuck together instead of breaking apart. Over millions of years, these gentle mergers produced protoplanets, embryonic worlds hundreds of kilometers across, which then gravitationally attracted even more material and continued to grow. This process is how Earth formed. It is how Venus formed. It is how Mars formed. It is the standard recipe for making a terrestrial planet. And it works beautifully, as long as the collisions remain slow and gentle. But in the zone that would become the asteroid belt, Jupiter's gravitational stirring changed everything. As Jupiter's core grew and its mass increased, its gravitational influence injected energy into the orbits of planetesimals throughout the belt region. Orbital resonances, positions where a small body's orbital period is a simple fraction of Jupiter's period, became zones of intense perturbation. Objects in these resonances were accelerated and flung onto highly eccentric, highly inclined orbits. Their relative velocities increased dramatically, and when objects moving at high relative velocities collide, they do not merge, they shatter. The construction project became a demolition. Instead of building a planet, the collisions in the belt broke apart the very bodies that were trying to grow. The raw material was not just halted, it was actively destroyed, ground down over hundreds of millions of years from large protoplanets to smaller fragments to the rubble field we see today. The total mass of the asteroid belt has been reduced by a factor of roughly 1,000 from its original value. Once, there may have been enough material between Mars and Jupiter to build several Earths. Now there is barely enough to build a single modest-sized asteroid, and yet, amid all that destruction, a handful of objects survived. A few protoplanets, formed early enough and grown large enough to withstand the increasing violence around them, managed to persist. They were battered, they were scarred, they lost much of their original mass, but they did not break apart entirely. Ceres survived. It grew to 940 kilometers in diameter, large enough to be rounded by its own gravity, large enough to be classified as a dwarf planet. Vesta survived. It reached 525 kilometers across and, remarkably, differentiated so completely that it developed an iron core, a rocky mantle, and a basaltic crust, a miniature version of Earth's internal structure. And Pallas survived. At 512 kilometers, it was almost as large as Vesta, but fundamentally different in character, darker, more primitive, more mysterious, and far more violently displaced from its original orbit. These three objects are not merely big rocks. They are protoplanets. They are the solar system's failed experiments, embryonic worlds that represent the earliest stage of planetary formation, frozen in time at the moment the process was cut short. They are, in a very real sense, fossils of creation. And among these three surviving protoplanets, Pallas is the one that raises the most questions. To appreciate the sheer scale of Pallas, consider this. If you could somehow stand on its surface, assuming you could find a flat spot among the thousands of craters that scar its landscape, you would weigh almost nothing. The surface gravity of Pallas is roughly 1/50th of Earth's gravity. A person who weighs 80 kilograms on Earth would weigh less than 2 kilograms on Pallas. You could jump 20 meters into the air with a casual effort. You could throw a baseball and watch it puff slowly over the close horizon, disappearing from view in just a few seconds, because the world beneath your feet curves so sharply. And yet, despite this minuscule gravity, Pallas holds together. It is massive enough that its own gravity has pulled it into an approximately spherical shape, though not perfectly so. Its dimensions are slightly irregular, roughly 550 kilometers along its longest axis and 478 along its shortest, giving it a slightly flattened appearance, like a ball that has been gently squeezed. This triaxial shape carries information about its interior, its rotation, and its history of impacts, information that scientists have been trying to decode from Earth for more than 2 centuries. The surface area of Pallas is approximately 800,000 square kilometers. That number sounds abstract until you compare it to geography, 800,000 square kilometers is larger than Turkey. It is larger than France. It is roughly the combined area of Texas and California. If Pallas were a country, it would be one of the 30 largest nations on Earth by area. And every square kilometer of that surface is unexplored, unknown, waiting. No human eye has ever seen its landscape in detail. No spacecraft instrument has ever mapped its mineral deposits or measured the depth of its craters from orbit. It is one of the largest unexplored territories in the entire solar system. Pallas has a density of about 2.9 grams per cubic centimeter. That number tells a remarkable story. Pure rock, the kind of silicate minerals that make up most asteroids, has a density of roughly 3.3 grams per cubic centimeter. Pure water ice has a density of about 0.9. Pallas sits between these values, which means it is not pure rock. It contains a significant fraction of water, locked inside hydrated minerals, chemically bound to the crystal structures of its rocky material, and possibly persisting as subsurface ice in its deep interior. This is not liquid water. It is not flowing. It is water that has been imprisoned in stone for billions of years, a fossil of the conditions that existed in the solar system when Pallas was born. The fact that Pallas and Ceres were discovered so close together in time was not a coincidence. It was a consequence of a mathematical prediction. In 1772, the German astronomer Johann Daniel Titius had noted a curious numerical pattern in the spacing of the known planets. Johann Elert Bode later popularized this pattern, now known as the Titius-Bode law, which predicted that there should be a planet at approximately 2.8 astronomical units from the Sun in the gap between Mars and Jupiter. When William Herschel discovered Uranus in 1781 at a distance that closely matched the law's next predicted value, the pattern seemed too precise to be coincidental. The search for the missing planet at the predicted distance intensified. A group of astronomers, sometimes called the Celestial Police, organized themselves to systematically search the zodiac for the missing body. Piazzi discovered Ceres before their coordinated search could begin, and Olbers found Pallas during his follow-up observations of Ceres. The rapid succession of these discoveries created a philosophical crisis. The Titius-Bode law predicted one planet, not two, and the crisis only deepened when Carl Ludwig Harding discovered a third body, Juno, in 1804, and Olbers himself found a fourth, Vesta, in 1807. Four objects where there should have been one. Olbers proposed an elegant solution. Perhaps there had originally been a single planet at the predicted distance, and it had been destroyed by some catastrophic event, an internal explosion or a colossal collision, leaving behind fragments that now orbited the Sun individually. This exploded planet hypothesis was compelling in its simplicity and troubling in its implications. If planets could be destroyed, the solar system was a more violent and unstable place than the clockwork universe envisioned by Newton and Laplace. The hypothesis persisted for decades, influencing the way astronomers thought about the region between Mars and Jupiter. It was not until the late 19th and early 20th centuries, as more and more asteroids were discovered and the total mass of the asteroid belt was found to be far too small to account for a planet-sized body, that the exploded planet hypothesis was definitively abandoned. The total mass of the entire asteroid belt, all of it combined, is less than 4% of the mass of the Moon. There was never a planet here. The belt is not debris from destruction. It is debris from failed construction, the raw materials of a planet that was never allowed to assemble. The reason for this failure is Jupiter, the largest planet in the solar system, with a mass 318 times that of Earth, formed quickly and catastrophically early in the solar system's history. Current models suggest that Jupiter's core, a body perhaps 10 to 20 times the mass of Earth, assembled within the first 1 to 3 million years after the Sun ignited, and it then rapidly accreted a massive envelope of hydrogen and helium gas from the surrounding nebula. This rapid formation had profound consequences for the asteroid belt. Jupiter's enormous gravity stirred the orbits of the planetesimals in the belt region, increasing their relative velocities to the point where collisions became destructive rather than constructive. Instead of gently merging and growing larger, the proto-asteroids smashed into each other at kilometers per second, shattering and eroding rather than accreting. The building process that created Earth, Mars, and the other rocky planets was aborted in the asteroid belt before it could reach completion. Pallas is one of the largest survivors of this aborted process. It grew to 512 kilometers before the gravitational stirring of Jupiter made further growth impossible. It is a fossilized embryo, a world that was on its way to becoming something larger and was stopped. And the fact that it survived at all, that it was not ground down to rubble by billions of years of collisions, is a testament to its size. Below a certain threshold, asteroids are fragile, easily shattered and dispersed. Above that threshold, the self-gravity of the body is strong enough to hold it together even through tremendous impacts. Pallas, at 512 kilometers, sits comfortably above that threshold. It has been battered, cratered, and scarred, but it has not been broken. This water content tells us something profound about where Pallas formed. In the early solar nebula, the disk of gas and dust from which the planets condensed, there was a critical boundary called the snow line. Inside the snow line, closer to the Sun, temperatures were too high for water ice to survive. The forming planets in this hot inner zone were built primarily from rock and metal, which is why Mercury, Venus, Earth, and Mars are dense, rocky worlds. Beyond the snow line, temperatures were cold enough for water to freeze into solid ice, and this ice became a major building block, a raw material that contributed to the formation of the outer solar system's icy moons, the cores of giant planets, and the vast population of comets. The snow line in the early solar system was located at roughly 2.7 astronomical units from the Sun, and Pallas orbits at an average distance of 2.77 astronomical units. It sits almost exactly at the ancient snow line. This is not a coincidence. It means that Pallas formed in the most important transitional zone in the entire solar nebula, the narrow boundary between the dry inner solar system and the wet outer solar system, the dividing line that determined whether a forming world would be made of rock or ice. That makes Pallas a witness, a frozen sample of conditions at the most critical boundary in the solar system during the most important period of its formation. It carries information about the temperature, the chemistry, and the dynamics of the protoplanetary disk at the exact location where the nature of the forming worlds changed from rocky to icy, and we have never been able to examine it up close. The surface of Pallas is dark, extraordinarily, startlingly dark. It reflects only about 12% of the sunlight that falls upon it, making it one of the dimmest large objects in the asteroid belt. By comparison, Vesta reflects roughly 42% of incoming light, gleaming almost white in telescope images. The Moon, which appears bright in our night sky, reflects about the same fraction as Pallas, around 12%. And freshly laid asphalt on a highway reflects about 4%. Pallas is somewhere between the Moon and a parking lot. From a distance, it would appear as a dull, dark sphere, barely visible against the blackness of space. This darkness is a clue. It suggests that the surface of Pallas is rich in carbon-bearing minerals, complex organic compounds, and hydrated silicates, materials that are associated with the most primitive, least thermally altered building blocks of the solar system. Carbonaceous chondrite meteorites, among the most ancient and scientifically valuable rocks ever found on Earth, have similar compositions and similar darkness. These meteorites contain amino acids, the building blocks of proteins. They contain pre-solar grains, microscopic particles older than the Sun itself, and some researchers believe that Pallas may be the parent body of a particular subclass of these meteorites, the B-type carbonaceous chondrites, which would make it one of the most important objects in the solar system for understanding the origin of organic chemistry and possibly the origin of life. But despite all of this darkness, all of this primitive chemistry, Pallas shows evidence of having undergone at least partial differentiation, the internal layering process that separates a body into a dense core and a lighter outer shell. On Earth, differentiation is what gave us an iron core, a rocky mantle, and a thin crust. On Vesta, differentiation was so thorough that the asteroid developed a clear iron core, a olivine-rich mantle, and a basaltic crust made of solidified lava, a structure so planet-like that Vesta is sometimes called the smallest terrestrial planet. But on Pallas, the evidence suggests something more ambiguous. The density of 2.9 grams per cubic centimeter is consistent with a partially differentiated interior, one where some separation of heavy and light materials has occurred. But the process did not go to completion. Pallas appears to have heated up enough to begin melting and separating, but not enough to finish the job. The heat source for this partial differentiation was almost certainly the decay of short-lived radioactive isotopes, particularly aluminum-26, a radioactive form of aluminum that was abundant in the early solar system. Aluminum-26 has a half-life of only about 717,000 years, which means it decays quickly and releases its energy over a relatively short period. If Pallas formed early enough, within the first 2 to 3 million years of the solar system, it would have incorporated enough aluminum-26 to generate significant internal heating. That heating would have begun to melt the interior, allowing heavy iron-rich material to sink toward the center and lighter silicate material to rise. But if Pallas formed even slightly later than objects like Vesta, the aluminum-26 would have already decayed significantly, producing less heat and resulting in less complete differentiation. This timing sensitivity is remarkable, a difference of just 1 or 2 million years in formation time, out of a total solar system age of 4.6 billion years, could explain the difference between Vesta's fully differentiated structure and Pallas's partially differentiated one. Pallas may have formed just late enough to miss the window of maximum radioactive heating, leaving it in a halfway state, neither fully primitive nor fully evolved. It is a world caught in the act of becoming something it never had the chance to be. The rotation of Pallas adds another layer of intrigue. Pallas spins on its axis once every 7.81 hours, a rotation period that is neither unusually fast nor unusually slow for an asteroid of its size. But its axial tilt, the angle between its rotation axis and the perpendicular to its orbital plane, is enormous. Pallas's axis is tilted at roughly 84 degrees, meaning it essentially rotates on its side, like a top that has nearly fallen over. This extreme axial tilt means that Pallas's poles alternately point almost directly toward the Sun and almost directly away from it as it orbits. Over the course of its 4.62-year orbital period, each pole experiences a prolonged period of continuous sunlight, followed by a prolonged period of continuous darkness, a pattern of extreme seasons unlike anything experienced by any planet in the solar system except Uranus, which also rotates nearly on its side. This extreme axial tilt raises its own set of questions. Was Pallas always tilted this dramatically, or was it knocked over by one of the massive impacts that scarred its surface? If one of those 400-kilometer impact basins was created by a collision energetic enough to excavate nearly 80% of the asteroid's diameter, it may well have been energetic enough to dramatically alter the spin axis. The axial tilt of Pallas, like its orbital inclination, may be a scar from an ancient catastrophe, written not in craters but in the geometry of rotation itself. But here is where things begin to get truly complicated. And this is the point where the story of Pallas transforms from an interesting scientific curiosity into something more troubling, more confusing, and far more consequential than most people realize. To understand what went wrong with Pallas, to understand why it orbits the way it does, and why its surface looks the way it does, and why its very existence presents a challenge to our models of how the solar system formed, we need to go back to the very beginning. Not the beginning of astronomy, not the beginning of human curiosity about the sky, the beginning of everything. 4.6 billion years ago, in a cold, dark corner of one of the Milky Way's spiral arms, something happened that would ultimately lead to every world, every ocean, every living thing, and every curious mind that has ever looked up at the stars. A cloud of gas and dust, mostly hydrogen and helium but laced with heavier elements forged in the nuclear furnaces of long-dead stars, began to collapse under its own gravity. The trigger may have been a nearby supernova, a dying star that exploded with the energy of 1 billion suns, sending a shockwave rippling through the surrounding interstellar medium with enough force to compress the cloud past its critical threshold. Or it may have been the slow, patient accumulation of density over millions of years, a gradual thickening that eventually crossed the tipping point between stability and collapse. Either way, once it began, the process was irreversible. Gravity, the weakest of the 4 fundamental forces, but the most relentless, the most patient, the one that never stops pulling, took over. As the cloud contracted, it began to spin faster and faster, the same way a figure skater accelerates when pulling their arms tight against their body. Conservation of angular momentum, one of the most inviolable laws of physics, demanded it. The collapsing material could not simply fall straight inward. It was forced to rotate, and as it rotated, it flattened. The cloud that had been roughly spherical was squeezed by its own spinning motion into a vast, thin disk, like a ball of dough being pressed into a pizza by invisible hands. Most of the mass, roughly 99.86% of it, accumulated at the center of this disk, where it formed a dense, hot ball of hydrogen that grew hotter and hotter as more material piled on. When the temperature at the core reached approximately 10 million degrees Celsius, hydrogen nuclei began fusing into helium, releasing an enormous flood of energy. The Sun was born, and the remaining fraction of the disk, that thin sliver of leftover material representing barely 1/7 of the total mass, became the raw material from which every planet, every moon, every asteroid, and every comet in the solar system would form. This disk, called the protoplanetary disk or the solar nebula, was not uniform. It had structure, it had temperature gradients, it had density variations. Closer to the Sun, where temperatures soared above 1,500 degrees Celsius, Only the most heat-resistant materials could exist in solid form. Iron, nickel, aluminum oxide, and silicate minerals rich in magnesium and calcium. These refractory materials condensed out of the hot gas like snowflakes forming in a winter storm. Except these snowflakes were made of metal and rock. Farther from the sun, where temperatures were cooler, additional materials could solidify, and beyond a critical distance of roughly 2.7 astronomical units, the temperature dropped below about 170 degrees Celsius below zero, cold enough for water to freeze into solid ice. This boundary, the snow line, was one of the most consequential features of the entire solar nebula. Inside the snow line, the forming planets could only incorporate rock and metal. Outside it, they could also incorporate enormous quantities of water ice, which was far more abundant than rock in the primordial disk. The presence of ice roughly tripled or quadrupled the amount of solid material available for building planets, which is why the outer solar system produced enormous worlds with massive cores surrounded by thick atmospheres of captured gas, while the inner solar system produced smaller, denser, rocky planets. And Pallas formed right at this boundary, right at the line where rock met ice, right at the edge of the most important transition in the entire disk. That positioning alone would make it a scientifically valuable object. But its positioning is only the beginning of the puzzle. Within the protoplanetary disk, solid particles began to stick together through a process that started microscopically and ended planetarily. Dust grains, each one smaller than a grain of sand, collided at gentle speeds and adhered through electrostatic forces, the same kind of force that makes a balloon stick to a wall after you rub it on your hair. These tiny aggregates grew into centimeter-sized pebbles. The pebbles grew into boulders. The boulders accumulated into kilometer-sized bodies called planetesimals, and the planetesimals, now large enough to exert meaningful gravitational attraction on each other, began merging through a combination of physical collisions and gravitational capture. This process, known as accretion, worked beautifully in most parts of the solar system. It was slow but steady, a patient assembly line building worlds one collision at a time. In the inner disk, within the first 10 million years or so, the accretion process produced a population of roughly 50 to 100 planetary embryos, each one roughly the size of Mars or the Moon, scattered throughout the zone where the terrestrial planets would eventually form. These embryos then collided with each other in a series of giant impacts over the next 100 million years, gradually merging into the 4 rocky planets we know today. Earth itself is the product of at least one, and possibly several, of these titanic collisions, the last and most dramatic of which is believed to have created the Moon. In the outer solar system, the process was even more efficient because of the additional ice beyond the snow line. The cores of the giant planets grew quickly, reaching 10 to 20 times the mass of Earth within just a few million years, at which point they became massive enough to gravitationally capture the surrounding hydrogen and helium gas. Jupiter, in particular, grew with extraordinary speed. Its core may have reached critical mass within the first 1 to 3 million years of the solar system's existence, making it one of the oldest objects in the entire system. But here is the problem. The very speed of Jupiter's formation, the rapidity with which it accumulated mass and extended its gravitational dominion, created a catastrophe in the region between its orbit and the orbit of Mars. The asteroid belt was caught in the crossfire. As Jupiter's mass increased, its gravitational influence grew correspondingly stronger and reached correspondingly farther. Orbital resonances began to appear throughout the belt, locations where a small body's orbital period was a simple rational fraction of Jupiter's own period. An object orbiting at the 3-to-1 resonance, for instance, completes exactly 3 orbits of the Sun for every 1 orbit of Jupiter, which means it receives a gravitational kick from Jupiter at the same point in its orbit over and over again. These repeated kicks are not random. They accumulate, they add up, and over thousands or millions of orbits, they pump energy into the small body's orbit, increasing its eccentricity and inclination until the orbit becomes unstable, and the object is either ejected from the belt entirely or sent crashing into another body. These resonances carved gaps in the asteroid belt, visible today as regions conspicuously devoid of asteroids, the so-called Kirkwood gaps, named after the American astronomer Daniel Kirkwood, who first identified them in 1866. They also increased the average velocity of collisions throughout the belt. In the inner solar system, where Jupiter's influence was weaker, planetesimals collided at speeds of perhaps a few meters per second, slow enough to merge. In the asteroid belt, Jupiter pumped those speeds up to several kilometers per second, fast enough to shatter. The result was a massacre. Instead of building a planet, the asteroid belt tore itself apart. Objects that had been growing for millions of years were broken back down into fragments. The total mass of the belt was depleted by a factor of roughly 1,000, ejected from the solar system or ground into dust. The planet that should have formed between Mars and Jupiter was murdered in its crib by the gravitational bully next door. But here is the critical point. A few objects survived. A handful of protoplanets, formed early enough and grown massive enough to withstand the increasing violence, persisted through the chaos. Ceres, Vesta, and Pallas. And among these three survivors, Pallas is the strangest. Because, while Ceres and Vesta, despite being battered and depleted, retained orbits that are broadly consistent with the general gravitational perturbation expected from Jupiter, Pallas did not. Pallas ended up on an orbit that is wildly, dramatically, almost impossibly inclined. An orbit that has no simple explanation within the standard model of asteroid belt evolution. The standard model explains the belt's depletion. It explains the Kirkwood gaps. It explains why Ceres and Vesta have moderately elevated inclinations. But it struggles with Pallas. Getting an object as massive as Pallas, more than 200 billion kilograms, onto an orbit inclined at nearly 35 degrees requires a specific, powerful, and finely tuned gravitational event, not just the general stirring of Jupiter's influence. For decades, planetary scientists proposed various mechanisms. Perhaps Pallas was scattered by a close gravitational encounter with a large planetary embryo that once existed in the belt but has since been destroyed or ejected. This is possible in principle, but the encounter would need to be remarkably precise, delivering enough energy to change the inclination dramatically without also ejecting Pallas from the belt entirely or sending it crashing into Mars or Jupiter. Perhaps Pallas was captured from a different region of the solar system altogether, formed at a different distance, and then gravitationally relocated to its current orbit. This too is possible, but it requires even more specific conditions, and it gets worse. In 2019, a team of researchers led by Michael Marset at the Massachusetts Institute of Technology published a groundbreaking study that added layers of complexity to the Pallas mystery. Using adaptive optics on the European Southern Observatory's Very Large Telescope in the Atacama Desert of Chile, they obtained the most detailed images of Pallas ever captured from Earth. The adaptive optics system corrects for the blurring caused by Earth's atmosphere, sharpening the telescope's vision to near its theoretical limit. The resulting images, while still far less detailed than what a visiting spacecraft could achieve, were sharp enough to reveal the overall shape of Pallas and the distribution of its largest surface features. What they found was extraordinary. Pallas was savagely cratered, more heavily cratered relative to its size than almost any other large body in the asteroid belt. The research team counted the number and size of visible craters and compared them to the crater populations on Ceres and Vesta. Pallas had 2 to 3 times more craters per unit area than Vesta, despite the two bodies being roughly the same diameter. The surface of Pallas was not just old, it was beaten, pulverized, hammered by billions of years of collisions at speeds that far exceeded the average for the rest of the belt. And the reason was clear. Pallas's extreme orbital inclination does not merely place it at an unusual angle. It turns the asteroid into a projectile. Twice during every 4.62-year orbit, Pallas crosses the ecliptic plane, the zone where the majority of the belt's population resides, and it crosses at a steep angle, moving at a high velocity, relative to the slower-moving, low-inclination asteroids that populate the midplane. The average collision speed on Pallas is approximately 41,000 kilometers per hour. On Vesta, That number is closer to 22,000. The difference is not subtle. It means that every impact on Pallas releases roughly 3.5 times as much energy per kilogram of impactor as an equivalent impact on Vesta. The same rock hitting Pallas does nearly 4 times the damage it would do hitting Vesta. The Marset team also identified something that stopped them cold. 2 enormous impact basins, each roughly 400 kilometers across, dominated the surface. These basins were so large that each one spanned nearly 80% of the asteroid's total diameter. An impact that produces a crater 400 kilometers wide on a body 512 kilometers across is not a minor event. It is a near-catastrophic one. The impactors that created those basins came dangerously close to shattering Pallas entirely, breaking it into fragments, the way the impact that created the Vesta family shattered a chunk of that asteroid's southern hemisphere. Pallas survived, but barely, and the scars remain, testament to a lifetime of violence. But here is what makes this truly terrifying. Those giant impact basins are not anomalies. They are not freak occurrences. They are the inevitable consequence of Pallas's orbit. Any body traveling on such a steeply inclined path through the asteroid belt will experience a relentless bombardment for as long as the belt exists. Pallas has been crossing the ecliptic, punching through the cloud of debris and absorbing impacts at extraordinary speeds for 4.5 billion years. The 2 giant basins we can see from Earth are just the most dramatic examples of a process that has been grinding away at Pallas's surface for nearly the entire history of the solar system. This bombardment has consequences that extend far beyond the craters themselves. Each major impact on Pallas blasts enormous quantities of material off its surface into space. This ejected debris enters orbits similar to Pallas's own and creates what astronomers call the Pallas family, a group of smaller asteroids that share similar orbital characteristics and are thought to be fragments chipped off the parent body by past collisions. The Pallas family includes hundreds of known objects, some just a few kilometers across, others tens of kilometers wide. These fragments, over millions and billions of years, have had their orbits slowly altered by the gentle but persistent pressure of sunlight, a phenomenon called the Yarkovsky effect. As these fragments absorb sunlight on one side and radiate heat from the other, the asymmetric thermal emission produces a tiny but continuous thrust that gradually changes their orbits. Over millions of years, this effect can push fragments into orbital resonances with Jupiter, which then fling them onto entirely new trajectories, some of which cross the orbit of Earth. There is a real possibility, supported by spectroscopic analysis of both Pallas and meteorite collections, that some of the carbonaceous chondrite meteorites found on Earth originated from Pallas. They were blasted off its surface by ancient impacts, drifted through interplanetary space for millions or billions of years, encountered one of Jupiter's resonances, were flung toward the inner solar system, and eventually entered Earth's atmosphere as fireballs, landing as dark, fragile, carbon-rich stones in deserts and fields and oceans around the world. If this is true, then humanity may already possess pieces of Pallas. We may have been holding fragments of this enigmatic protoplanet in museum collections and laboratory drawers for decades without knowing their true origin. But having a handful of meteorites, even if they could be definitively traced back to Pallas, is vastly different from visiting the source. Meteorites are altered by their long journey through space, bombarded by cosmic rays that change their isotopic composition, heated by their passage through Earth's atmosphere at speeds of tens of thousands of kilometers per hour, fractured by the shock of deceleration, and contaminated by terrestrial water, organic matter, and weathering. The information they carry is valuable, but it is incomplete, filtered, degraded. To truly understand Pallas, to decode its internal structure, map its surface composition in detail, determine its water content and distribution, identify the minerals on its surface, and resolve the question of whether it experienced partial differentiation. We need to go there. We need to send a spacecraft. And as we have already established, that is extraordinarily difficult. The delta V required to match Pallas's orbit is enormous. The engineering challenges are daunting. The cost is prohibitive. Several mission concepts have been proposed over the years, including flybies, orbiters, and even sample return missions, but none have progressed beyond the study phase. Pallas remains, as of today, one of the most scientifically important objects in the solar system that has never been visited by a spacecraft. Something is wrong with our assumptions. Something is wrong with the clean, orderly story we tell about how the solar system formed. The real history was not orderly. It was not clean. It was chaotic, violent, and full of catastrophes. And Pallas, that silent, battered, tilted world drifting through the darkness between Mars and Jupiter, may be one of the most important pieces of evidence we have for understanding just how wild that history truly was. The question is no longer just what happened to Pallas. The question is what happened to the entire solar system, and the answer begins with a model so dramatic, so violent, and so counterintuitive that when it was first proposed in 2005, it struck many scientists as almost too extreme to be real. A model in which the giant planets did not stay where they formed. A model in which Jupiter and Saturn did not simply sit in their orbits and watch the inner solar system evolve. A model in which the giant planets migrated, wandering through the solar system like wrecking balls, reshaping everything in their path, scattering asteroids, destabilizing orbits, and triggering a cataclysm that reshaped the entire architecture of the solar system hundreds of millions of years after its formation. The model is named after the French city of Nice, where the research group that developed it was based. And what it describes is nothing less than the most violent restructuring event in the solar system's history, since its formation from the protoplanetary disk. The Nice model proposes something that, when you first hear it, sounds almost absurd. It suggests that the four giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form in the orbits they currently occupy. Instead, they formed in a much more compact configuration, all clustered together in the outer solar system, much closer to the Sun and much closer to each other than they are today. Beyond their orbits, extending outward for billions of kilometers, was a massive disk of icy planetesimals, remnants of the planet-forming process that had not been incorporated into any of the giant planets. For hundreds of millions of years, this configuration was stable. The giant planets orbited peacefully, the outer disk of icy bodies sat quietly, and the inner solar system went about its business. But the arrangement was not truly stable. It was metastable, like a ball balanced on the tip of a pencil. It could remain balanced for a long time, but the slightest perturbation would send it tumbling. The perturbation came from the outer disk. Gravitational interactions between the giant planets and the nearby icy bodies slowly, imperceptibly altered the planet's orbits over millions of years. Jupiter crept inward, toward the Sun. Saturn crept outward, and at some point, perhaps 3.9 billion years ago, perhaps 4.1 billion years ago, the exact timing is still debated, Jupiter and Saturn crossed a critical orbital resonance. Their orbital periods briefly locked into a 2-to-1 ratio, with Jupiter completing exactly 2 orbits for every one of Saturn's. The consequences were immediate and catastrophic. The resonance amplified the gravitational interactions between the two most massive planets in the solar system, destabilizing the entire outer planetary system. Saturn was pushed outward. Uranus and Neptune, caught in the gravitational upheaval, were scattered violently. One or both of them may have been flung through the outer disk of icy planetesimals, disrupting it completely and sending billions of comets and ice chunks streaming inward toward the Sun and outward toward interstellar space. The late heavy bombardment, a period of intense cratering on the Moon, Earth, and the other inner planets that occurred roughly 3.9 billion years ago, may be a direct consequence of this event, and here is where Pallas enters the picture. The Nice model does not only affect the outer solar system, the migration of Jupiter, even by a modest amount, has devastating consequences for the asteroid belt. When Jupiter moves inward, even slightly, the locations of its orbital resonances shift. Resonances that were previously in empty regions of the belt suddenly sweep across zones that were populated with asteroids. Objects that have been orbiting stably for hundreds of millions of years suddenly find themselves in regions of intense gravitational perturbation. Their orbits become unstable. Their inclinations and eccentricities spike. Some are ejected from the belt entirely. others are driven onto orbits that cross the paths of the inner planets. Several research groups have investigated whether the NICE model instability could explain the orbit of Pallas. The results are tantalizing, but inconclusive. Some simulations produce objects on highly inclined orbits similar to Pallas's, but the probability is low. Getting a body as massive as Pallas onto an inclination of nearly 35 degrees remains difficult even with the added dynamism of the NICE model. Other factors may be needed, perhaps a close encounter with a now lost planetary embryo, perhaps a resonance sweeping event of a specific type, perhaps a combination of mechanisms operating in sequence. The challenge is not simply one of energy. In principle, there is more than enough gravitational energy available during a giant planet migration event to fling an asteroid onto a highly inclined orbit. The challenge is one of specificity. The inclination excitation mechanism must be powerful enough to tilt the orbit of a massive protoplanet by 35 degrees, while simultaneously failing to eject it from the solar system entirely. This is a narrow window. Most bodies that receive enough gravitational perturbation to reach such extreme inclinations are pushed further still onto hyperbolic trajectories that send them careening out of the solar system forever, joining the vast, cold population of interstellar vagabonds that drift between the stars. Pallas, somehow, received exactly the right amount of perturbation, enough to dramatically tilt its orbit, but not enough to unbind it from the Sun. One mechanism that has received particular attention is secular resonance sweeping. As Jupiter and Saturn migrated toward their current orbital positions, the locations of their secular resonances, the orbital configurations where their long-term gravitational effects accumulate most strongly, swept through the asteroid belt like invisible walls of force. A secular resonance passage can dramatically increase an asteroid's inclination or eccentricity over timescales of tens of thousands to millions of years, gradually pumping energy into the orbit without the sudden violence of a close encounter. If one of these sweeping resonances passed through the region where Pallas was orbiting, it could have slowly lifted its inclination to its current extreme value. The appeal of this mechanism is that it explains not just the high inclination, but also the survival. A secular resonance sweep is a gradual process, one that nudges rather than shoves. It could have elevated Pallas's inclination incrementally, allowing the protoplanet to remain gravitationally bound to the solar system, even as its orbit became progressively more extreme. But testing this hypothesis requires knowing the exact migration history of Jupiter and Saturn, with a precision that current models do not provide. The details of when the migration began, how long it lasted, how smoothly the giant planets moved, and whether there were periods of rapid versus slow migration all affect the pattern of resonance sweeping and therefore the final orbital distribution of the asteroids. What is clear is that the orbit of Pallas is not simply the result of Jupiter sitting in its current position and stirring the belt. Something more dramatic happened. Something that involved large-scale rearrangement of the solar system's architecture. And Pallas, with its wild orbit, its battered surface, its primitive composition, and its partially differentiated interior, carries the evidence of that event within its very structure, like a witness to a crime who cannot speak, but whose injuries tell the whole story. The violence of that story is written in statistics. The Marset study's finding that Pallas's crater density is 2 to 3 times higher than Vesta's is not merely a quantitative difference. It is a qualitative one. It means that the surface of Pallas has been subjected to a bombardment regime fundamentally different from that experienced by any other large body in the asteroid belt. The high inclination acts as a multiplier of destruction. When Pallas plunges through the midplane, it encounters the densest concentration of other asteroids at relative velocities that turn every collision into a catastrophe, a typical main belt collision between two objects on low inclination. Low eccentricity orbits might occur at 5 to 8 kilometers per second. On Pallas, the average impact velocity is roughly 11.5 kilometers per second, 41,000 kilometers per hour, nearly double the belt average. The energy of an impact scales as the square of the velocity. Doubling the impact speed quadruples the energy. This means that a given impactor striking Pallas releases roughly 4 times more energy than the same impactor striking an asteroid on a more typical orbit. The craters are larger, the ejector is thrown farther, and the damage to the target body is more severe. Over 4.5 billion years, this compounding effect has transformed Pallas's surface into a record of destruction unmatched by any comparable body. And the two enormous impact basins, each stretching nearly 400 kilometers across, represent collisions of almost unimaginable violence, events that must have shaken the entire protoplanet to its core and ejected billions of tons of material into space. The compositional puzzle deepens the mystery further when astronomers examine Pallas spectroscopically, analyzing the wavelengths of light it reflects and absorbs. They find a surface composition that does not neatly match any of the other large asteroids. Pallas is classified as a B-type asteroid, a subclass of the broader C complex, the carbonaceous asteroids. B-type asteroids are relatively rare. They are characterized by a flat to slightly blue-sloped reflectance spectrum in visible light, and by the presence of absorption features in the near-infrared that indicate hydrated minerals on the surface. But Pallas does not look exactly like other B-type asteroids. Its spectrum has subtleties that suggest a surface composition more complex than a simple mix of carbonaceous material and hydrated silicates. Some studies have detected features consistent with the mineral serpentine, a hydrated magnesium silicate that forms when olivine-rich rock is altered by liquid water. If serpentine is present on Pallas, it means that liquid water once existed inside this asteroid, at least transiently, in the early solar system. The water did not just sit passively in the crystal lattice of minerals. It flowed, it reacted with the rock. It chemically transformed the minerals through a process called aqueous alteration. This is a profound revelation. Pallas, this dark, distant, battered protoplanet, once had liquid water inside it. Not for long, perhaps, not in large quantities, perhaps, but long enough and abundant enough to alter the rock, to form new minerals, to leave a chemical signature that is detectable from hundreds of millions of kilometers away, using nothing more than reflected sunlight. The presence of aqueous alteration on Pallas connects it to a broader class of primitive solar system bodies, including carbonaceous chondrite meteorites, the asteroid Bennu visited by the OSIRIS-REx mission, and the asteroid Ryugu visited by Japan's Hayabusa 2 mission. All of these objects show evidence of early water activity, and all of them are thought to preserve clues about the conditions that prevailed in the outer regions of the protoplanetary disk during the first few million years of the solar system. But there is a crucial difference between Pallas and these other primitive bodies. Bennu is only about 500 meters across. Ryugu is roughly 900 meters across. They are rubble piles, loosely bound aggregates of fragments held together more by chance than by gravity. Pallas, at 512 kilometers, is a genuine protoplanet, massive enough to have experienced significant internal heating, differentiation, and geological evolution. It is not a rubble pile, it is a world. And the information locked inside it is correspondingly richer, more complex, and more difficult to obtain. Consider what we learned from visiting Bennu and Ryugu. The samples returned by OSIRIS-REx and Hayabusa 2 revealed remarkably detailed information about the chemistry of the early solar system. The presence of amino acids, of nucleobases, of presolar grains older than the Sun. Ryugu's samples showed evidence of extensive aqueous alteration, confirming that even small asteroids experience fluid flow in the earliest epoch of solar system history. And Bennu's surface turned out to be so loosely packed that the OSIRIS-REx sampling arm plunged deeply into it, revealing a body held together by little more than cohesion and rotation. Now imagine what we might learn from a body like Pallas, one that has 250 times the diameter of Bennu, one whose internal gravity was strong enough to drive differentiation, one whose formation at the snowline placed it at the exact transition between water-rich and water-poor chemistry. The difference in scientific return between visiting a rubble pile and visiting a protoplanet is not incremental. It is transformational. A rubble pile tells us about the ingredients of the solar system. A protoplanet tells us about the recipes, about how those ingredients were combined by heat and pressure and water into the geological processes that ultimately produced planets. The connection between Pallas and specific meteorite groups remains one of the most tantalizing and most frustrating puzzles in planetary science. The CM and CR carbonaceous chondrites, both water-rich and organically complex, have been proposed as possible Pallas-derived meteorites based on spectral similarities. But the spectral match is imperfect, complicated by the fact that a meteorite's journey through space and its violent entry through Earth's atmosphere can alter its surface chemistry and appearance. Terrestrial weathering further changes the samples after they land. What we measure in a laboratory on Earth may not precisely match what a spacecraft would measure on Pallas's surface, even if the meteorite genuinely originated from that body. This is the core frustration of Pallas science. We know enough about this asteroid to understand that it is extraordinarily important. We know that it formed at the snow line, the most critical boundary in the solar nebula. We know that it experienced aqueous alteration, meaning liquid water once existed inside it. We know that it partially differentiated, meaning its interior began to separate into layers. We know that its orbit was violently disturbed by some event in the early solar system. We know that its surface has been pulverized by billions of years of high-speed impacts, and we know that fragments of its surface may have reached Earth as meteorites. But we do not know the details. We do not know the full story. And until a spacecraft visits Pallas, we are left piecing together fragments of evidence, like archaeologists trying to reconstruct a civilization from a handful of pottery shards and a few lines of text. But here is what makes this truly terrifying. The story of Pallas is not just the story of one asteroid. It is the story of what happened to the solar system during the most violent and least understood period of its history. If we can understand Pallas, if we can decode its orbit and composition and internal structure, we may finally be able to understand the events that shaped the architecture of the entire planetary system, events that determined whether Earth would receive the water and organic materials necessary for life, events that determined whether the inner solar system would be hospitable or hostile, events that determined, in the most literal sense possible, whether we would exist at all. And we are only beginning to understand how to read the evidence that Pallas carries. The story of humanity's attempts to understand Pallas is a story of ingenuity, frustration, and the relentless push of technology against the limits of distance and physics. It is a story told in 5 chapters, each one representing a different era of investigation, a different approach to the problem, and a different lesson about what happens when science confronts an object that refuses to give up its secrets easily. The first chapter begins not with telescopes or spacecraft, but with mathematics and the naked eye. For most of the 19th century, Pallas was studied almost exclusively through the careful measurement of its position in the sky. Astronomers would spot the faint point of light moving slowly against the background stars, note its position with excruciating precision, and use those positions to refine their calculations of its orbit. This work was painstaking, tedious, and essential. Every observation was made by hand. Every calculation performed with pencil and paper. Every result checked and rechecked against the predictions of celestial mechanics. It was through these positional measurements, accumulated night after night, year after year, decade after decade, that the extraordinary inclination of Pallas's orbit was first established and confirmed. The key figure in this early era was Carl Friedrich Gauss, the same mathematical prodigy who had predicted the position of Ceres in 1801 using a revolutionary new method for orbit determination. After the discovery of Pallas by Olbers in 1802, Gauss turned his formidable intellect to the problem of calculating the new object's orbit, and found the task far more difficult than the calculation for Ceres had been. The reason was precisely the extreme inclination and eccentricity that make Pallas so unusual. Standard orbital calculation methods of the era, which assumed nearly circular, low-inclination orbits, because that was what most planetary objects exhibited, struggled with the wild trajectory of this second asteroid. The perturbations caused by Jupiter further complicated the problem, as the giant planet's gravity subtly but continuously altered Pallas's orbit in ways that were difficult to predict. Gauss was forced to develop more general and more powerful mathematical techniques to handle the problem. He refined his method of least squares, a statistical technique for finding the best fit to a set of noisy data points that is still one of the most widely used tools in all of science. He developed new approaches to perturbation theory, the mathematical framework for calculating how the gravity of one body affects the orbit of another, and he pushed forward the theory of elliptical integrals, the mathematics needed to describe motion along non-circular orbits. In a very real sense, Pallas made modern orbital mathematics necessary. Its strange orbit demanded better tools, and those tools, once created, opened up the study of comets, asteroids, and eventually spacecraft trajectories for the next 2 centuries. The asteroid that refused to behave like other objects in the sky forced mathematics itself to become more sophisticated. It is one of the earliest examples of a pattern that repeats throughout the history of science. An anomalous observation drives the development of new theory, and the new theory proves useful far beyond the original problem that inspired it. Gauss determined that Pallas orbited the Sun with a period of approximately 4.62 years at an average distance of about 2.77 astronomical units, with an inclination of roughly 34 degrees and an eccentricity of about 0.23. These numbers, first calculated from handwritten observations of a faint moving dot seen through a modest telescope in the early 19th century, have been refined over 2 centuries of increasingly precise measurements, but never fundamentally changed. Gauss got it right. His mathematical genius, stimulated by the intractable orbit of a strange new asteroid, produced tools that would serve astronomy for generations. But for all the elegance of the orbital calculations, the physical nature of Pallas remained almost entirely unknown throughout the 19th century and well into the 20th. It was a point of light, nothing more. Its size could be estimated only crudely, based on its brightness and an assumed value for its surface reflectivity. Its shape was unknown. Its composition was unknown. Its surface features were invisible. Its mass could only be guessed at. For more than 150 years after its discovery, Pallas was essentially a set of orbital parameters attached to a dim speck of light, a ghost with a trajectory but no body. The second chapter opens in the 1970s and 1980s with the advent of infrared astronomy and the development of spectroscopic techniques, sensitive enough to analyze the faint reflected light from asteroids. This was an era of transformation in planetary science. New detectors, new telescopes, and new analytical methods were opening windows onto objects that had been featureless dots for generations. And for the first time, scientists could do more than simply track Pallas's position against the stars. They could begin to determine what it was actually made of. The technique is conceptually simple, but technically demanding. Every material absorbs and reflects light differently. By measuring the spectrum of light reflected from an asteroid, breaking that light into its component wavelengths, and measuring the intensity at each wavelength, scientists can identify the minerals and compounds present on the surface. Different minerals have different spectral fingerprints, distinctive patterns of absorption and reflection that betray their chemical identity. Infrared observations in the 1970s revealed that Pallas had a very low albedo, reflecting only about 12% of the sunlight that fell upon its surface. This immediately placed it in the category of dark, carbonaceous asteroids, chemically and physically distinct from the bright rocky asteroids like Vesta, which reflects more than 40% of incoming light. The darkness itself was informative. It suggested a surface rich in carbon compounds and opaque minerals, materials that absorb most of the light that strikes them and return very little to the observer. Spectroscopic analysis in the visible and near-infrared wavelengths revealed a relatively featureless spectrum with a slight blue slope, meaning that Pallas reflects slightly more blue light than red light. This spectral shape classified Pallas as a B-type asteroid within the broader C-complex of carbonaceous objects, a designation that would prove critical in linking Pallas to specific classes of primitive meteorites found on Earth. The classification was significant. C-complex asteroids are generally associated with primitive, undifferentiated material, the kind of stuff that has changed the least since the solar system formed. They are thought to be the parent bodies of carbonaceous chondrite meteorites, those dark, crumbly, carbon-rich stones that contain amino acids, presolar grains, and other materials from before the Sun was born. If Pallas was indeed a C-complex object, it meant that despite its large size, it might be composed of some of the most ancient, least processed material in the solar system. But the spectral data also hinted at something more complicated. Absorption features near a wavelength of 3 micrometers suggested the presence of hydrated minerals on the surface, minerals that had been chemically altered by interaction with liquid water at some point in Pallas's history. This was the first spectroscopic evidence that Pallas had experienced aqueous alteration, a process that requires liquid water to exist inside a body, at least temporarily. The math is striking. For liquid water to have existed on an object as cold and small as Pallas, significant internal heating must have occurred, most likely from the decay of radioactive aluminum-26 within the first few million years of the solar system. The spectral classification of Pallas also raised a puzzling question. If Pallas is a B-type carbonaceous asteroid, it should have a composition similar to a specific group of carbonaceous chondrite meteorites. Some researchers proposed a connection between Pallas and the CM-type carbonaceous chondrites, which are rich in hydrated minerals and show extensive evidence of aqueous alteration. Others suggested a link to the CR-type chondrites, which are less altered but still primitive. Still others argued that Pallas might be the parent body of a unique and rare class of meteorites that did not fit neatly into any existing category. The debate was never resolved because the spectral data from Earth, even with the best instruments of the era, lacked the resolution and wavelength coverage needed to make a definitive identification. The spectrum of Pallas was tantalizingly similar to several different meteorite types, but not a perfect match for any of them. This frustrating ambiguity would persist for decades and would become one of the strongest arguments for sending a spacecraft to Pallas for direct measurement. The third chapter is the story of the Hubble Space Telescope and later ground-based adaptive optics systems, both of which brought Pallas into sharper focus than had ever been possible before. This chapter spans roughly 2 decades, from the mid-1990s to the late 2010s, and it represents the period during which Pallas transformed from a spectral classification and a set of orbital elements into an actual world, with shape, features, and a surface that could be seen, however dimly. In the late 1990s and early 2000s, the Hubble Space Telescope was aimed at Pallas during several observing campaigns. Hubble orbits above Earth's atmosphere, which means its images are not blurred by the turbulent air that degrades ground-based observations. The telescope's wide field and planetary camera, and later its advanced camera for surveys, could resolve Pallas as a tiny disk rather than a point of light, provided the asteroid was near opposition, the point in its orbit when it is closest to Earth and most fully illuminated by the Sun. The Hubble images were revelatory despite their limited resolution. For the first time, the overall shape of Pallas could be measured directly rather than inferred from light curve variations, the periodic brightening and dimming as the asteroid rotates and presents different cross-sections to the observer. Hubble confirmed that Pallas was roughly oblate spheroidal, wider at its equator than at its poles, consistent with a body whose shape has been influenced by its rotation. The measurements also revealed that Pallas was significantly less spherical than Ceres, which is round enough to qualify as a dwarf planet, but more spherical than most smaller asteroids, which tend to have irregular, potato-like shapes. Pallas was caught in the intermediate zone, large enough for gravity to have pulled it toward a sphere, but not so large that gravity had completely won the contests against the structural strength of rock. The Hubble data also provided the first crude indications of albedo variations on the surface of Pallas. Some regions appeared slightly brighter than others, suggesting differences in mineral composition, surface texture, or the degree of space weathering. Space weathering is the gradual darkening and reddening of airless body surfaces caused by micrometeorite impacts and bombardment by solar wind particles and cosmic rays. Fresh, unweathered surfaces tend to be brighter, while older, more exposed surfaces are darker. If the albedo variations on Pallas were related to space weathering, They might indicate regions where recent impacts had exposed fresh material from beneath the darkened outer layer, but Hubble could only see so much. At the distance of Pallas, even Hubble's resolution allowed only the broadest features to be detected. Craters had to be hundreds of kilometers wide to be visible. Fine details were impossible. Pallas was still fundamentally a smudge, a better smudge than any ground-based telescope could produce, but a smudge nonetheless. The real breakthrough came from ground-based telescopes equipped with adaptive optics, and it came much later than anyone expected. Adaptive optics is a technology that uses deformable mirrors to correct for the blurring effects of Earth's atmosphere in real time. The system works by monitoring a bright reference point, either a natural star or an artificial laser guide star, and measuring how the atmosphere distorts the light from that reference. A computer then calculates the shape needed to cancel the distortion and deforms a thin, flexible mirror accordingly, hundreds or thousands of times per second. The result is an image nearly as sharp as what a space telescope could achieve, at a fraction of the cost. By the 2010s, adaptive optics systems on the world's largest telescopes had reached a level of sophistication that allowed them to produce images of bright asteroids with an angular resolution rivaling, and in some cases exceeding, what Hubble could achieve. The key advantage of these ground-based systems was aperture size. Hubble's primary mirror is 2.4 meters across. The European Southern Observatory's Very Large Telescope, located in the Atacama Desert of northern Chile, one of the driest and clearest places on Earth, has individual mirrors 8.2 meters across. Bigger mirrors collect more light and can resolve finer details, provided the atmospheric blurring can be corrected. The landmark study, the one that changed the way scientists thought about Pallas, came in 2019. Michael Marcet, then at the Massachusetts Institute of Technology, led a team that used the SPHERE instrument on the VLT to capture the most detailed images of Pallas ever obtained. SPHERE, an acronym for Spectropolarimetric High Contrast Exoplanet Research, was originally designed to image exoplanets orbiting other stars, but its extraordinary angular resolution and contrast capabilities made it an ideal tool for studying nearby solar system objects as well. The team observed Pallas during its closest approach to Earth, capturing a series of images over the course of several hours as the asteroid rotated. By combining these images and using sophisticated deconvolution algorithms to further sharpen them, they produced a three-dimensional model of Pallas's shape and a preliminary map of its largest surface features. The resolution was about 20 to 30 kilometers per pixel, still far less detailed than what a visiting spacecraft could achieve, but enough to reveal the overall character of the surface. What they found stunned the planetary science community. Pallas was covered in craters, not just a few large craters, as one might expect on any ancient body, but a dense, overlapping pattern of impacts that covered virtually every visible portion of the surface. The team counted and measured the craters they could identify and compared the results to the known crater populations on Ceres and Vesta. Pallas had roughly 2 to 3 times more craters per unit area than Vesta, despite the two bodies being approximately the same size, and Vesta's surface had already been considered heavily cratered based on the detailed mapping performed by NASA's Dawn spacecraft. Marcet and his colleagues ran extensive computer simulations to understand why Pallas was so much more heavily cratered than its neighboring protoplanets. They modeled the collision environment that Pallas experiences as a result of its extreme orbital inclination, calculating the frequency and velocity of impacts from the broader population of smaller asteroids in the belt. The simulations incorporated the known distribution of asteroid sizes, orbits, and velocities, and they tracked the statistical likelihood of Pallas encountering projectiles at various speeds and angles. The results confirmed what the images suggested and quantified it precisely. Pallas encounters other asteroids at average impact speeds of approximately 41,000 kilometers per hour. On Ceres, the average impact speed is roughly 26,000 kilometers per hour. On Vesta, roughly 22,000. The difference is enormous and has enormous consequences. Kinetic energy scales as the square of velocity. which means that doubling the impact speed quadruples the energy released. At 41,000 kilometers per hour, the kinetic energy of a typical impactor striking Pallas is roughly 3.5 times greater than the energy of the same impactor striking Vesta. More energy means bigger craters, more ejecta, more surface disruption, and more damage per impact. The study also raised a startling implication about the total mass Pallas has lost over its lifetime. The researchers estimated that the cumulative effect of billions of years of high-speed impacts had ejected roughly 1.5 to 2% of Pallas's total mass. That sounds like a small fraction, but remember that Pallas is enormous. 2% of its mass corresponds to roughly 4 billion kilograms of material, launched into space by impact after impact after impact. This ejected material formed the Pallas family of asteroids, a scattered population of fragments orbiting the Sun on trajectories similar to the parent bodies, carrying with them pieces of Pallas's surface and possibly its interior. The fourth chapter is the story of the missions that were proposed but never flew. It is in some ways the most frustrating chapter in the entire narrative of Pallas, because it is a story of ideas that were scientifically compelling, technically feasible, and ultimately rejected in favor of other priorities. The first serious mission concept targeting Pallas emerged in the early 2000s, when the success of NASA's near-Shoemaker mission to the asteroid Eros demonstrated that asteroid rendezvous missions were both practical and scientifically productive. Near-Shoemaker, launched in 1996 and arriving at Eros in 2000, spent a year orbiting the asteroid, mapping its surface in unprecedented detail, and eventually landing on it in a controlled descent. The mission proved that spacecraft could navigate to orbit and study asteroids with great success, and it inspired a wave of new mission proposals targeting a wide range of asteroids, including Pallas. Several concepts were developed. One proposed a flyby mission that would use a series of gravity assists from Earth and Mars to swing the spacecraft onto a trajectory that would bring it within a few hundred kilometers of Pallas. The encounter would be brief, lasting only a few hours, but during that window, the spacecraft's cameras and spectrometers would capture images and compositional data far more detailed than anything obtainable from Earth. The advantage of a flyby is simplicity and cost. The spacecraft does not need to carry enough fuel to slow down and enter orbit. The disadvantage is that the encounter is fleeting and most of the surface remains unobserved. Another concept proposed an orbital mission, modeled on NASA's Dawn spacecraft, which used ion propulsion to orbit both Vesta and Ceres. An ion-propelled Pallas orbiter would carry a comprehensive payload of instruments, including cameras, spectrometers, a magnetometer, and a gravity science package, and would spend months or years in orbit, mapping the entire surface and measuring the internal structure through gravitational field analysis. The ion drive would allow the spacecraft to gradually match Pallas's orbit, climbing slowly out of the ecliptic plane over a period of years. But the numbers were daunting. The delta V required to reach and orbit Pallas using ion propulsion was significantly higher than what Dawn had needed to visit Vesta and Ceres, and Dawn had been one of the most ambitious missions in the history of the Discovery program. A Pallas orbiter would need either a larger solar array to power a more aggressive ion drive, or a longer cruise phase, or both. Cost estimates consistently placed such a mission at the upper end of the Discovery-class budget, and in competition with proposals to visit more accessible and arguably more immediately compelling targets like metallic asteroids, active asteroids, and Jupiter's Trojan asteroids. The competition problem is crucial and often underappreciated by the public. Space agencies do not choose missions in isolation, they choose between missions. Every proposal submitted to NASA's Discovery or New Frontiers programs is evaluated against every other proposal, and the selection criteria include not only scientific merit but technical readiness, cost realism, schedule confidence, and risk. A Pallas mission, no matter how scientifically compelling, must compete against missions to targets that are easier to reach, cheaper to study, and that answer equally important questions about different aspects of the solar system. In NASA's Discovery selection rounds, Proposals targeting Pallas have struggled not because the science is weak, but because the engineering is demanding and the flight time is long. A typical Pallas orbiter mission using current ion propulsion technology would require a cruise phase of 6 to 8 years, followed by a primary science mission of at least 1 year. That is a decade-long commitment from concept to completion, requiring sustained institutional support, continuous funding, and a team willing to dedicate a significant portion of their careers to a single objective. In a funding environment where budgets are constrained and political priorities shift on timescales of 2 to 4 years, decade-long missions face inherent institutional headwinds. There is also the radiation environment to consider. Pallas orbits at an average distance of 2.77 astronomical units from the Sun. At that distance, the solar flux is only about 1/7 of its value at Earth's orbit. A solar-powered spacecraft at Pallas must carry much larger solar arrays to generate the same power as a mission operating closer to the Sun. And larger arrays mean more mass, more cost, and more mechanical complexity. Nuclear power sources, specifically radioisotope thermoelectric generators, could solve the power problem, but the supply of plutonium-238, the isotope used in space power systems, is limited and is allocated preferentially to flagship missions like those to the outer solar system. Despite these obstacles, the scientific case for a Pallas mission has only grown stronger over time. Each new observation raises more questions than it answers. Each new piece of the puzzle reveals a more complex and more important picture. And among the planetary science community, there is a growing recognition that Pallas represents an irreplaceable target, a unique window into conditions and processes that no other body in the solar system preserves. A third concept, the most ambitious of all, proposed a sample return mission. The spacecraft would rendezvous with Pallas, collect material from its surface using a touch-and-go mechanism similar to what OSIRIS-REx used at Asteroid Bennu, and then return the sample to Earth for laboratory analysis. Such a mission would provide definitive answers about Pallas's composition, mineralogy, and connection to known meteorite groups. It would allow scientists to measure isotopic ratios, determine the age of the surface material, identify organic compounds, and characterize the water content with precision impossible from remote observations. But the cost and complexity of a sample return from Pallas's extremely inclined orbit placed it firmly in the flagship class category, competing for funding with missions to Europa, Enceladus, and Titan, targets with direct connections to the search for extraterrestrial life. None of these missions were selected. As of today, no space agency has approved a mission to Pallas. The asteroid continues to orbit in scientific isolation, studied only from afar. The fifth chapter brings us to the present day and to the most recent advances in remote observation. In the absence of a spacecraft mission, planetary scientists have continued to push the boundaries of what can be learned about Pallas from Earth and from Earth orbit, using every tool at their disposal with a determination that borders on obsession. In 2020, a team led by researchers at the Paris Observatory used data from the European Space Agency's Gaia mission to refine the orbit and mass of Pallas with unprecedented precision. Gaia is a remarkable spacecraft. Launched in 2013 and positioned at the second Lagrange point, a gravitationally stable location roughly 1.5 million kilometers from Earth in the direction away from the Sun, Gaia's primary mission is to map the positions and motions of more than 1 billion stars in the Milky Way with exquisite accuracy. But, as it scans the sky, Gaia also observes thousands of asteroids as they drift through its field of view. By precisely measuring the positions of background stars as Pallas passed near them, the Gaia team was able to detect an almost imperceptibly tiny shift in the stars' apparent positions, a shift caused by the gravitational deflection of starlight by Pallas's mass. This technique, called astrometric mass determination, is essentially the same principle that Einstein predicted in his general theory of relativity. Mass bends space, and bent space deflects light. On the scale of an asteroid, the deflection is minuscule, measured in millionths of an arcsecond, but Gaia's instruments are precise enough to detect it. The result was the most accurate mass measurement of Pallas ever obtained from remote observations. The mass was determined to be approximately 2.04 times 10 to the 20th kilograms, with an uncertainty of less than 1%. Combined with a refined shape model from the Marset study, this mass yielded a density of approximately 2.92 grams per cubic centimeter, confirming previous estimates and tightening the constraints on Pallas's internal composition and structure. This density measurement is a powerful tool for understanding what lies beneath the surface. A density of 2.92 grams per cubic centimeter is consistent with several possible internal configurations, but it rules out many others. It is too low for a body composed entirely of anhydrous silicate rock, which would have a density closer to 3.3. It is too high for a body with a large fraction of ice or void space in its interior. It is most consistent with a mixture of rocky silicate minerals and hydrated minerals, with some possible contribution from a small iron-rich core. If Pallas is partially differentiated, with a modestly denser core and a lighter, more hydrated outer layer, the observed bulk density can be reproduced, but the specific proportions remain uncertain. Models that include a small iron core surrounded by a hydrated silica mantle fit the data. So do models with no iron core but a gradient in hydration and porosity. Without seismic data from a surface station or a detailed gravity field measurement from an orbiting spacecraft, the models cannot be distinguished. Thermal observations have added another piece to the puzzle. The Spitzer Space Telescope, which operated from 2003 to 2020, observed Pallas at mid-infrared wavelengths during several campaigns. These observations measured the thermal emission from the asteroid surface, the heat radiated outward as the sun-warmed rock cools. The thermal data revealed that Pallas's surface has a thermal inertia consistent with a regolith-covered body, a surface blanketed in fine-grained debris created by billions of years of impacts. The thermal inertia value, a measure of how quickly the surface heats up and cools down, was lower than that of bare rock, but higher than that of extremely fine lunar-style dust, suggesting a mixture of particle sizes and perhaps some degree of compaction or cementation. The James Webb Space Telescope, which began scientific observations in 2022, has opened new possibilities for studying Pallas and other asteroids at infrared wavelengths with sensitivity and spectral resolution far exceeding anything previously available. Early observations of other C-complex asteroids with WST have revealed spectral features related to water ice, organic molecules, and specific clay minerals that were invisible to previous instruments. If JWST can observe Pallas with sufficient time and wavelength coverage, it may be able to identify mineral species on the surface with unprecedented specificity, potentially resolving the long-standing debate about which meteorite group, if any, represents Pallas's composition. There is also the possibility of studying Pallas through stellar occultations, events in which Pallas passes directly between Earth and a distant star. During an occultation, the star's light is briefly blocked by the asteroid, and the timing of the blockage, measured from multiple sites across a chord of the asteroid's shadow, reveals the asteroid's size and shape with extraordinary precision. Several stellar occultations by Pallas have been observed, most notably events in 2006, 2017, and 2019, involving networks of amateur and professional observers spread across thousands of kilometers. The chords measured during these events have confirmed the overall dimensions of Pallas and provided independent verification of the shape model derived from adaptive optics imaging. The power of occultation observations lies in their extraordinary geometric precision. When a star is occulted, the timing of the disappearance and reappearance can be measured with millisecond accuracy. At the relative velocity of the shadow crossing the Earth's surface, typically 20 to 40 kilometers per second, this timing precision translates to a spatial resolution of tens of meters along the chord, far better than any other remote sensing technique available for main belt asteroids. Multiple observers spread across the shadow path produce multiple chords, and the collection of these chords traces the asteroid's silhouette at the instant of the occultation. Over multiple events, observed from different geometries as the asteroid presents different aspects of its rotating body, a three-dimensional shape can be reconstructed. The limitation of occultation observations is their rarity and unpredictability. A given star is occulted by a given asteroid only when their orbits align as seen from a specific location on Earth, an event that may occur only once in a decade or less for a particular combination. Predicting occultations requires precise knowledge of both the asteroid's orbit and the star's position, and even small errors in either can shift the predicted shadow path by hundreds of kilometers, causing observers to miss the event entirely. The rise of high-precision stellar catalogues, particularly the Gaia catalogue, with its sub-milliarcsecond astrometry, has dramatically improved occultation predictions in recent years, enabling more reliable observations and larger, better coordinated observer networks. Another emerging technique involves radar astronomy. Planetary radar, using facilities like the now-defunct Arecibo Observatory or the Goldstone Deep Space Communications Complex, can bounce radio signals off nearby asteroids and use the returned echoes to map their shapes and surface properties with meter-scale resolution. However, radar observations require the target asteroid to be relatively close to Earth, typically within about 0.1 astronomical units for the most detailed measurements. Pallas never approaches Earth closer than about 1.2 astronomical units, placing it well beyond the effective range of even the most powerful radar systems. This is yet another way in which Pallas's orbit conspires to keep its secrets hidden. It is always too far away for the one technique that could map its surface in exquisite detail from the ground. Perhaps the most intriguing recent development involves the study of Pallas family asteroids, those fragments blasted off the parent body and scattered through the belt. By spectroscopically observing these smaller fragments and comparing their compositions to both Pallas and known meteorite types, researchers are building a more complete picture of the compositional diversity within the Pallas family. Some fragments appear spectrally similar to the parent body, suggesting they come from the surface or shallow subsurface. Others show subtle spectral differences that might indicate they were excavated from deeper layers, exposing material with a different degree of thermal processing or aqueous alteration. If different Pallas family members come from different depths within the protoplanet, they collectively provide a cross-section of Pallas's interior, a natural drill core produced by the impacts that created them. This approach, studying the parent body through its scattered fragments, is imperfect and indirect, but it is the best available strategy in the absence of a dedicated mission. It is a kind of cosmic forensics, reconstructing the victim's internal anatomy from the debris scattered at the scene. The story of the scientific investigation of Pallas is a story told across 2 centuries and 5 chapters of ever-improving technology, from the hand-calculated orbits of Gauss to the adaptive optics images of Marset, from the spectral classifications of the 1970s to the gravitational measurements of Gaia. Each chapter has brought new information and new questions. Each advance in technology has peeled back another layer of mystery, revealing a world more complex, more battered, and more important than the previous generation of instruments could have imagined. And yet, after all of this work, after 224 years of observation and analysis, the most fundamental questions about Pallas remain unanswered. What is its internal structure? Is it differentiated or not? How much water does it contain? What are the exact minerals on its surface? When did the giant impacts occur? And what specific sequence of events flung it onto its extreme orbit? These are not idle curiosities. They are questions whose answers would reshape our understanding of how the solar system formed, how water was distributed among the forming planets, and how the conditions for life were established on Earth. The frustration of knowing this and being unable to reach the answers is one of the defining emotions of modern Pallas science. There is a moment in every deep exploration of the cosmos when the investigation turns inward, when the facts stop being abstract and start pressing against something personal, when you realize that the object you have been studying is not just an object, it is a mirror, and what it reflects back is your own existence, your own fragility, your own place in a universe that is far older, far stranger, and far more violent than anything you were prepared for. Pallas is that kind of object, and the deeper truth it reveals is not merely about an asteroid. It is about the nature of planetary birth, the role of chaos in creating worlds, and the razor-thin margin between existence and oblivion that characterizes everything in the solar system, including Earth. Let us step back and consider what we have learned. We know that the solar system formed from a collapsing cloud of gas and dust 4.6 billion years ago. We know that within that cloud, a disk of material flattened out around the young sun and began to condense into solid particles, then boulders, then planetesimals, then protoplanets, and finally, in some cases, full-grown planets. We know that this process worked smoothly in some regions of the disk, but failed catastrophically in others. We know that Jupiter, the most massive planet, formed quickly and wielded its gravitational influence like a weapon, preventing the formation of a planet in the asteroid belt and scattering the bodies that lived there onto chaotic orbits. And we know that Pallas survived all of this. It survived the accretion era, when gentler collisions allowed it to grow to 512 kilometers across. It survived Jupiter's gravitational assault, which depleted the belt of 99.9% of its original mass. It survived the possible upheaval of the nice model instability, when the giant planets migrated and reshuffled the architecture of the solar system. It survived billions of years of high-speed impacts as its extreme orbit carried it repeatedly through the most dangerous regions of the asteroid belt. It survived impacts so violent that they excavated craters nearly as wide as the asteroid itself. Pallas should not exist, not in its current form, not in its current orbit. The probability of an object this large, on an orbit this extreme, surviving intact for 4.5 billion years is genuinely low, and yet here it is, orbiting, enduring, carrying within its battered body a record of events that no other object in the solar system preserves in quite the same way. Let that sink in. Consider what it means. Every planet, every moon, every world that we have studied in detail has been modified, resurfaced, and transformed by billions of years of geological activity. Earth has plate tectonics that constantly recycle its crust. Mars had volcanoes that buried its earliest surface under kilometers of lava. Venus has been entirely resurfaced by global volcanic eruptions within the last few hundred million years. Even the Moon, geologically dead for billions of years, has been significantly modified by the lava flows that filled its giant impact basins and created the dark maria visible to the naked eye. But Pallas is different. Pallas has no internal heat source driving geological activity. It has no atmosphere to erode its surface. It has no plate tectonics, no volcanoes, no water flowing across its terrain. The only process that has significantly modified its surface since the end of the accretion era is impact cratering, the relentless bombardment of objects striking its surface at tens of thousands of kilometers per hour. And while those impacts have certainly altered the surface, they have done so in a way that preserves information rather than destroying it. Craters are records. Each one tells a story. The size of a crater reveals the energy of the impact. The depth reveals the strength of the surface material. The distribution of craters across the surface reveals the directionality and frequency of impacts. The presence or absence of degraded, eroded craters tells us about the rate of surface modification. On a body like Pallas, where no geological process other than cratering has been active for billions of years, the crater record is a nearly complete history of the collisional environment in the asteroid belt, stretching back to the very earliest days of the solar system. And it gets stranger. The craters on Pallas are not just records of impacts, they are windows into the interior. When a large impactor strikes Pallas, it excavates material from deep beneath the surface, bringing buried minerals and compositions up into view. The interiors of large craters on Pallas may expose material that has been shielded from space weathering and cosmic ray bombardment for billions of years, material that preserves the original composition of the protoplanet's interior layers. If Pallas experienced partial differentiation, as the density data suggests, then the walls and floors of its deepest craters might reveal the boundary between the primitive outer layer and the more processed interior, a geological contact that records the moment when the asteroid's internal heating ceased and the differentiation process froze in place. A spacecraft orbiting Pallas and imaging its craters in detail could potentially map the internal structure of a protoplanet without ever drilling beneath the surface. The impacts have already done the excavation. Nature has already performed the core sample. All we need to do is look. But the implications of Pallas extend far beyond its own surface. Consider the fragments that have been blasted off Pallas by billions of years of impacts. The Pallas family of asteroids, those hundreds of smaller objects orbiting the Sun on trajectories similar to Pallas's own, represent a scattered archive of material from different depths and locations on the protoplanet's surface. Some of these fragments may come from the ancient, primitive outer layer. Others may come from deeper, more processed material exposed by the giant impact basins. Each fragment carries a piece of Pallas's story, and collectively they represent a three-dimensional sampling of the asteroid's composition that no single surface measurement could provide. And some of those fragments, as we have discussed, may have reached Earth as meteorites. If the connection between Pallas and certain carbonaceous chondrite meteorites can be confirmed, it would mean that we already possess samples of a protoplanet that formed at the snow line of the solar nebula 4.6 billion years ago. We would have pieces of a world that witnessed the transition from the dry inner solar system to the wet outer solar system, a world that experienced liquid water in its interior within the first few million years of the solar system's existence, a world that began to differentiate into layers, but stopped before the process was complete. Let that sink in. We might already have pieces of this world sitting in museum drawers and laboratory refrigerators around the planet. We might have been studying fragments of Pallas for decades without realizing their true significance. And the key to unlocking that significance, the test that would confirm or deny the connection, requires detailed measurements of Pallas itself, measurements that can only be obtained by a visiting spacecraft. There is a deeper truth embedded in the story of Pallas, one that transcends the specifics of asteroid science and touches on something more fundamental. It is the truth about how precarious existence really is. The solar system we live in, the orderly arrangement of planets orbiting a stable star, the benign environment that has allowed life to flourish on Earth for nearly 4 billion years, was not inevitable. It was not the only possible outcome of the process that began when that cloud of gas and dust collapsed 4.6 billion years ago. It was one outcome among many possible ones, shaped by a sequence of events that could easily have gone differently. If Jupiter had formed a little earlier or a little larger, its gravitational influence might have extended further inward, disrupting the formation of Mars or even Earth. If the nice model instability had been more severe, it might have destabilized the orbits of the inner planets entirely, sending one or more of them crashing into the Sun or ejecting them into interstellar space. If the late heavy bombardment, triggered by the migration of the giant planets, had been more intense, it might have sterilized Earth's surface so thoroughly that life could never have recovered. Every world in the solar system carries the scars of this violent history, but most of those scars have been covered over by subsequent geological activity. Earth's plate tectonics have erased all but the faintest traces of the late heavy bombardment. Mars's volcanoes have buried its earliest impact record under plains of basalt. The Moon's mere basalts have flooded many of its largest impact basins. Pallas, though, preserves those scars. It has no geology to erase them. Its surface is a palimpsest of impacts stretching back to the beginning, layer upon layer of craters recording the changing intensity and character of the collisional environment in the asteroid belt over the full sweep of solar system history. It is one of the few objects in the inner solar system where the complete record of the first billion years, the most violent and most important period, might still be readable. And there is something even deeper, something that connects the story of Pallas to the story of life itself. The water in Earth's oceans had to come from somewhere. Earth formed inside the snow line, in the hot inner region of the solar nebula, where water could not exist as ice. The building blocks of Earth were dry, and yet Earth has vast oceans, covering 70% of its surface to an average depth of 3.7 kilometers. Where did all that water come from? One of the leading hypotheses is that Earth's water was delivered by impacts from water-rich objects that originated beyond the snow line. Comets are one candidate, but their isotopic signatures do not perfectly match Earth's water. A better match comes from carbonaceous asteroids, objects that formed near the snow line and incorporated water into their mineral structures. Objects like Pallas. The implications are staggering. If Earth's water came from objects similar to Pallas, then Pallas is not just a scientific curiosity. It is a representative of the population of objects that made Earth habitable. It is a sample of the delivery mechanism that brought water to a dry world and made life possible. The same violent collisional environment that battered Pallas for billions of years also generated the fragments that drifted inward and delivered water, and possibly organic molecules, to the young Earth. Every glass of water you drink may contain molecules that were once part of an object like Pallas. Every ocean on Earth, every river, every raindrop, every living cell may owe its existence to the water that was locked inside protoplanets at the snowline 4.5 billion years ago. We are, in a very real and measurable sense, connected to Pallas, not metaphorically, not poetically, chemically, atomically. And Pallas itself does not know this. It does not know that it matters. It orbits in silence, in cold, in darkness, enduring impact after impact, shedding pieces of itself into space, carrying within its ancient body the answers to questions that the universe has no interest in asking. Only we ask those questions. Only we look up and wonder. Only we have built the telescopes and the spacecraft and the mathematics necessary to even begin understanding what Pallas is and why it matters. That is the deeper truth. It is not just about an asteroid. It is about the extraordinary improbability of creatures arising on a small rocky planet, assembling civilizations, developing science, building telescopes, and then pointing those telescopes at a faint speck of light that turns out to be a fossil of their own origin. We are made of the same material that Pallas is made of. The iron in our blood was forged in the same supernova, whose shockwave triggered the collapse of the cloud that became our solar system. The carbon in our cells, the oxygen we breathe, the water in our bodies, all of it traces back to the same protoplanetary disk from which Pallas condensed. We are not studying a foreign object. We are studying a distant relative, a sibling that took a different path, a path that led not to oceans and continents and life, but to cold, dark silence and a surface of craters. And the difference between our path and its path was not predetermined. It was not inevitable. It was the result of a specific sequence of gravitational encounters, resonance crossings, and chaotic perturbations that could easily have gone differently. Consider the scale of this contingency. The solar system contains roughly 2 million asteroids larger than 1 kilometer in diameter. Of those, only 3 are protoplanets large enough to preserve detailed records of the earliest era of planetary formation: Ceres, Vesta, and Pallas. 3 objects out of 2 million. And of those 3, Pallas is the only one that formed at the snow line, the only one with a primitive carbonaceous composition, and the only one on an orbit extreme enough to have been shaped by the most violent events in the solar system's dynamical history. It is unique. There is nothing else like it, anywhere in the belt, anywhere in the inner solar system, anywhere within reach of current or near-future spacecraft technology. If Pallas were to be destroyed tomorrow, struck by an impactor large enough to shatter it completely, the information it carries would be lost forever. The record of snowline conditions in the first few million years of the solar system, the evidence of early aqueous alteration, the compositional signature of the protoplanetary disk at its most critical boundary, all of it would be scattered into fragments too small to tell the story. The window of opportunity to study this object is not permanent. It has already been open for 4.5 billion years, which might seem like plenty of time, but in terms of human civilization's ability to study it, the window has only been open for a little over 2 centuries, and we have not yet walked through it. There is a concept in conservation biology called an irreplaceable species, an organism so unique in its genetic heritage and ecological role that its loss would represent a gap in the tree of life that could never be filled. Pallas is an irreplaceable asteroid. Its loss would represent a gap in the solar system's record of its own formation that could never be filled by any other object. And unlike an endangered species, which at least has advocates and conservation programs and public awareness, Pallas has almost no public profile at all. It orbits in obscurity, known to planetary scientists but virtually unknown to everyone else, waiting for a mission that may never come. The existential weight of this situation is difficult to convey. We live in a solar system that is gradually losing its memory. Every geological process, from volcanic eruptions to plate tectonics to atmospheric erosion, destroys ancient surfaces and overwrites old information with new. The Moon's oldest surfaces are being gradually darkened and degraded by micrometeorite bombardment and solar wind implantation. Even the asteroid belt itself is slowly evolving, as collisions break large objects into smaller ones, and the Yarkovsky effect gradually shifts orbits and removes bodies from the belt entirely. The record of the solar system's formation is fading, slowly but inexorably, like a photograph left in sunlight. Pallas is one of the last places where a substantial portion of that record might still be readable. Its surface, battered as it is, preserves craters and compositional signatures dating back to the beginning. Its interior, insulated by 4.5 billion years of accumulated regolith, may preserve mineral assemblages that have not been exposed to space since the solar system was young. It is a time capsule from the age of planet formation, sealed by gravity and cold and the sheer difficulty of reaching it. And we stand on the edge of being able to open it. The technology exists. The science case is overwhelming. The propulsion systems are within reach. What is lacking is not capability but priority, not knowledge but will. And that is perhaps the most unsettling realization of all, that the obstacle between us and the secrets of our own origin is not physics or engineering, but funding and institutional inertia. If the solar system's dice had rolled just slightly differently, it might be Pallas that hosts life, and Earth that drifts as a frozen, battered ruin through the asteroid belt. The margin between planet and protoplanet, between living world and dead rock, is thinner than we ever imagined. What makes Pallas irreplaceable, in a way that no other single object in the solar system is the combination of its characteristics. Other asteroids formed at the snow line. Other asteroids experienced aqueous alteration. Other asteroids have high orbital inclinations. But no other asteroid combines all of these properties with the sheer size and mass of a protoplanet. Pallas is big enough to have experienced geological processes, internal heating, fluid flow, mineral transformation, partial differentiation. It is primitive enough to have retained the chemical signatures of those processes rather than having them erased by later volcanism or complete melting. And its orbit, as punishing as it is from a mission design perspective, has preserved it in a kind of dynamic isolation, keeping it away from the most crowded regions of the belt and reducing the likelihood that it would be shattered by a collision with another large body. This combination of size, composition, location, and orbital history makes Pallas a uniquely valuable scientific target. It is not the easiest asteroid to visit. It is not the most photogenic. It is not the one with the catchiest name or the most dramatic backstory in the popular press. But it may be the single most informative object in the entire asteroid belt, the one body whose detailed study would answer the most questions about the most important processes in the most critical period of the solar system's history. And there is yet another layer to this realization. Pallas is not merely a passive witness to the solar system's violent history. It is an active participant. The fragments blasted from its surface by billions of years of impacts did not simply vanish. They entered orbits of their own. They drifted through the solar system. They were nudged by sunlight pressure and gravitational resonances onto new trajectories. And some of them crossed the orbit of Earth. We know that carbonaceous meteorites have been falling to Earth for as long as Earth has existed. We know that these meteorites carry water, amino acids, and other organic molecules. We know that the early Earth was bombarded by such objects during the late heavy bombardment, a period of intense impact activity that coincides with the emergence of the first evidence of life in the geological record. The timing is suggestive, the chemistry is suggestive, and the possibility that Pallas contributed to this life-enabling bombardment is not speculation. It is a scientifically testable hypothesis, one that could be confirmed or refuted by a dedicated mission to the asteroid. If confirmed, it would mean that Pallas is not just a relic of the past. It is part of our origin story. It is a character in the narrative of how life arose on Earth. Not because it is alive, not because it ever was alive, but because pieces of it may have delivered the raw materials that made life possible on a world that started out as a ball of dry, hot rock. Consider the chain of causation. A cloud of gas and dust collapses. A star ignites. A disk of debris forms. Within that disk, trillions of dust grains stick together, building up larger and larger bodies. In one region, near the snow line, a protoplanet grows to 512 kilometers across. Its interior heats up. Water flows inside it, altering its minerals and creating hydrated compounds. Then Jupiter's gravity intervenes, halting its growth and eventually scattering it onto a wild inclined orbit. For the next 4.5 billion years, that protoplanet is bombarded by other asteroids, each impact chipping off fragments that drift inward through the solar system. Some of those fragments enter Earth's atmosphere and land as dark, carbon-rich stones, and the water and organic molecules they carry become part of Earth's oceans, part of Earth's chemistry, part of the molecular soup from which the first self-replicating molecules, and eventually the first cells, emerge. The staggering thing about this chain is how fragile it is. If the snowline had been located slightly farther from the Sun, the protoplanet would have formed with a different composition, perhaps more ice-rich, perhaps less chemically complex. If Jupiter had formed more slowly, the protoplanet might have continued growing, accreting enough mass to become a full planet, and its material would never have been scattered as fragments across the inner solar system. If the giant planet migration had occurred at a slightly different time, or with a slightly different intensity, the protoplanet might have been ejected entirely from the solar system, its water and organics lost forever to interstellar space. At every stage of the process, from the initial condensation to the final delivery of water to Earth, there were branching paths that could have led to a radically different outcome. This is not science fiction. This is the actual physical chain of events that may connect a battered asteroid between Mars and Jupiter to the existence of every living organism on this planet. Every bacterium, every plant, every animal, every human being who has ever lived may owe some fraction of their existence to material that was once part of a protoplanet that never became a planet. That is the deeper truth of Pallas. It is not just an object. It is a thread in the fabric of our origin, woven so deeply into the story that most of us never notice it, never think about it, never consider that the water in our cells might trace its lineage back to a world that orbits in silence and cold and darkness, 400 million kilometers away, seen only as a faint dot of light in our most powerful telescopes. There is a quietness to this realization that makes it different from the usual revelations of astronomy. It does not involve the biggest numbers or the most distant objects or the most violent explosions. It involves a connection, a link between here and there, between now and then, between the living and the ancient. And that connection, once seen, cannot be unseen. It changes the way you think about water, about rock, about the sky, about the night, about the vast dark spaces between the planets, where old worlds drift and old stories wait to be told. We have traveled a long way tonight. We have gone from a point of light noticed by a German physician on a cold March night in 1802 to the edge of what modern science can tell us about one of the most extraordinary objects in the solar system. We have traced the arc of discovery from the handwritten calculations of Carl Friedrich Gauss to the adaptive optics images of the Very Large Telescope. We have watched as Pallas was classified, reclassified, forgotten, and rediscovered by successive generations of scientists, each one peeling back another layer of mystery to reveal a world stranger and more important than the last generation imagined. And now it is time to step back and ask what all of this means. Not for the history of astronomy, not for the future of space missions, but for us, for the way we understand our own existence in a universe that is far older, far more violent, and far more interconnected than our everyday experience suggests. The first and most immediate implication of the Pallas story is this. The solar system we inhabit today is not the solar system that formed 4.6 billion years ago. The neat arrangement of planets orbiting a stable star, the orderly progression from rocky inner worlds to gas giants in the outer reaches, the seemingly timeless architecture that we take for granted. All of it is the product of billions of years of violent reshuffling. Planets migrated, orbits shifted, giant worlds careened through regions they never should have visited, scattering asteroids and comets like billiard balls, triggering bombardments that cratered every surface in the inner solar system, and fundamentally altering the distribution of water and organic molecules among the forming worlds. Pallas is a survivor of this chaos, not a passive bystander who happened to avoid the worst of the destruction, but an active participant who was caught in the crossfire, battered beyond anything we see on comparable objects, flung onto an orbit so extreme that no spacecraft has ever been able to reach it, and left to endure billions of years of relentless high-speed impacts. And yet it survived, it held together. Its ancient body, forged in the first few million years of the solar system's existence, endured every catastrophe the cosmos threw at it, and is still orbiting today, still carrying its secrets, still waiting. The second implication is more personal, and it is the one that tends to stay with people long after they have forgotten the orbital parameters and the spectral classifications. It is this: we may owe our existence to objects like Pallas, Earth formed dry, the building blocks of our planet condensed from the hot inner regions of the protoplanetary disk, where temperatures were too high for water ice to survive. The early Earth was a ball of molten rock and metal, with no oceans, no atmosphere to speak of, and no liquid water on its surface. Everything that makes Earth habitable, the vast blue oceans that cover 70% of its surface, the complex organic molecules that form the basis of all known life, the volatile compounds that fill the atmosphere, all of it had to be delivered from somewhere else. The most likely delivery mechanism is impact. Objects from beyond the snowline, water-rich asteroids and comets that had formed in the cooler outer regions of the disk, were scattered inward by the gravitational upheavals of the early solar system and crashed into the young Earth, depositing their water and organics on its surface. The late heavy bombardment, that intense period of impact activity, roughly 3.9 billion years ago, that may have been triggered by the nice model instability, would have been the peak of this delivery process. Billions of water-rich impactors, many of them chemically similar to objects like Pallas, pounded the inner solar system for hundreds of millions of years. If this picture is correct, then every ocean on Earth, every lake, every river, every raindrop, every cell in every living organism contains water that was once part of the solar nebula's snowline region. Water that condensed onto dust grains 4.6 billion years ago. Water that was incorporated into planetesimals and protoplanets like Pallas. Water that was chemically bound into hydrated minerals by the same aqueous alteration process that we detect spectroscopically on Pallas's surface today. Water that was liberated from its rocky prison by the heat and pressure of impact, vaporized, condensed, and eventually collected in the basins that would become Earth's oceans. We are not separate from the solar system. We are not observers looking at the cosmos from outside. We are participants. We are made of the same material. And the water that sustains every form of life on this planet was delivered by a process in which objects like Pallas played a central and possibly indispensable role. The third implication concerns the nature of knowledge itself. The story of Pallas is, at its core, a story about the limits of what we can know and the lengths to which we will go to push those limits further. For 224 years, scientists have been studying this object with every tool available to them, from naked-eye observations to space telescopes to mathematical models of extraordinary complexity. And after all of that effort, after centuries of accumulated work, the most basic questions about Pallas remain unanswered. We do not know what the inside of Pallas looks like. We do not know whether it has an iron core. We do not know exactly what minerals cover its surface. We do not know when the giant impact basins were formed. We do not know what specific event put it on its extreme orbit. We do not even know, with certainty, whether the meteorites we think came from Pallas actually did. We do not know whether the aqueous alteration was global or localized, whether liquid water permeated the entire interior or flowed only in restricted channels near heat sources. We do not know whether the partially differentiated interior has a sharp boundary between core and mantle, or a gradual transition. We do not know whether any of the giant impact basins punched deep enough to expose material from the differentiated interior, creating windows into the protoplanet's hidden structure. We do not know what the regolith looks like at the scale of individual grains. Whether it is fluffy and porous like Ryugu's surface, or compacted and consolidated by billions of years of impact gardening, each of these unknowns represents not just a gap in data, but a missed opportunity for understanding. The internal structure of Pallas would tell us how much heat was generated by aluminum-26 decay in the first few million years, which would constrain when Pallas formed relative to the calcium-aluminum-rich inclusions that mark time zero of the solar system. The mineralogy of the surface would tell us the temperature and duration of aqueous alteration, which would constrain the water budget of snowline protoplanets. The ages of the impact basins would tell us when the most violent collisions occurred, which would constrain the timing and intensity of the late heavy bombardment. Every measurement, every data point, would cascade through a chain of inferences that connects this one asteroid to the broadest questions in planetary science. This is humbling, not in the deflating sense of realizing how little we know, but in the motivating sense of realizing how much there still is to discover. Every unanswered question about Pallas is a door waiting to be opened. Every gap in our understanding is an invitation to build a better instrument, design a more clever mission, or develop a more powerful theory. The story of Pallas is not finished, it is barely begun. And there is one more implication, the one that is hardest to articulate, but maybe the most important of all. It is the realization that the universe does not owe us its secrets. Pallas has been orbiting the Sun for 4.5 billion years. It will continue orbiting for billions more, whether or not we ever send a spacecraft to study it. The information it carries, the record of the solar system's formation, preserved in its craters and minerals and internal structure, is there regardless of whether anyone ever reads it. The universe is not a book written for us. It is a book that exists whether or not anyone opens it. But we can choose to open it. That is what makes us extraordinary. Not our size, which is insignificant on any cosmic scale. Not our lifespan, which is a flash compared to the age of a protoplanet. But our curiosity. Our ability to look at a faint point of light in the sky and ask what it is, where it came from, and what it can teach us about ourselves. That is what the story of Pallas ultimately reveals. Not just the nature of an asteroid, but the nature of the species that studies it. We are creatures who build telescopes and aim them at the darkness, who calculate orbits with pencil and paper and then refine them with spacecraft and lasers, who care, genuinely and deeply, about a world we have never touched and may never touch, not because it is useful, not because it is profitable, but because it is there, and because understanding it brings us one step closer to understanding everything. The connection between Pallas and Earth is not just chemical or physical, it is philosophical. It is the recognition that we are part of the same system, products of the same process, children of the same collapsing cloud of gas and dust. And the study of Pallas, however frustrating, however limited by technology and funding, and the sheer difficulty of reaching an asteroid on a tilted orbit, is ultimately the study of ourselves, of where we came from, of how we got here, of what we are made of. And that study is worth every telescope hour, every mission proposal, every sleepless night spent calculating orbital mechanics in a university office. Because the alternative, the choice not to look, not to ask, not to reach, is the only real failure. The night sky looks different once you know what is out there. Not just the stars, not just the familiar planets, tracking their slow paths along the ecliptic, but the things you cannot see, the things that are too faint, too distant, too small to register on the human eye, but that are there nonetheless, orbiting in silence, carrying within their ancient bodies the history of everything. Pallas is one of those things. A dark world, 512 kilometers across, orbiting the Sun at an angle that sets it apart from every other large body in the asteroid belt. A protoplanet that began the journey toward becoming a world like Earth and was stopped, frozen, left suspended in a state of incomplete transformation for 4.5 billion years. A surface so heavily cratered that it looks like a golf ball struck by a cosmic club, scarred by the relentless bombardment that comes from crossing the asteroid belt's midplane, at 41,000 kilometers per hour, twice every orbit, for longer than life has existed on our planet. It formed at the snow line, the most important boundary in the solar nebula, the dividing line between the dry inner solar system and the wet outer solar system. Its composition, dark and carbon-rich, and laced with hydrated minerals, tells us that it incorporated water into its very structure during the earliest days of the solar system's existence. Its density, 2.9 grams per cubic centimeter, tells us that it heated up enough to begin separating into layers, but not enough to complete the process. Its orbit, inclined at nearly 35 degrees, tells us that something violent happened to it, something that wrenched it off its original trajectory and flung it onto a path of perpetual punishment. No spacecraft has ever visited Pallas. No camera has ever captured its surface in detail. No instrument has ever sampled its dust or measured the composition of its craters from close range. It remains, after more than 2 centuries of observation, one of the most important unexplored worlds in the solar system, a fossil of creation, a witness to the solar system's most violent and least understood era, a potential source of the water and organic molecules that made Earth habitable, and it orbits in near total obscurity. Most people have never heard its name. Most astronomy textbooks devote only a paragraph or two to its existence. In the hierarchy of public fascination, it ranks far below Mars, far below Jupiter, far below even small asteroids that have been visited by spacecraft and given dramatic names and media attention. Pallas is the forgotten giant, the overlooked survivor, the third largest asteroid, hidden in plain sight. But what it represents is anything but small. Pallas represents the question of how planets form and why some of them fail. It represents the question of where Earth's water came from and how the ingredients for life were distributed through the inner solar system. It represents the question of what the solar system's early history really looked like, whether it was orderly and gradual or chaotic and violent, and how the architecture we see today emerged from the turbulence of the past. It represents the question of how we know what we know and how much remains to be discovered and whether we will choose to go looking. The title of tonight's journey asked about the mysterious third largest object in the asteroid belt, and the answer is this. Pallas is mysterious because it preserves information that no other object in the solar system preserves. It formed at the right place, at the right time, with the right composition to record the conditions at the most critical boundary in the protoplanetary disk. It was battered but not destroyed, altered but not erased, displaced but not lost. It is a protoplanet that never became a planet, a world that carries the memory of the solar system's birth, inside a body too remote and too strangely orbiting for us to have reached it yet. But the mystery is not eternal, it is solvable. The technology to send a spacecraft to Pallas exists. The scientific questions are clear, the instruments are proven. What is needed is the will, the funding, and the recognition that this forgotten world is worth the effort, that the secrets locked inside its dark, cratered body are worth the cost of climbing out of the ecliptic and matching an orbit that defies the conventions of the asteroid belt. One day, perhaps, a spacecraft will depart Earth on a long, curving trajectory that takes it out of the plane of the planets and into the tilted domain of Pallas. It will arrive after years of travel, its cameras will turn on, and for the first time in the history of human exploration, the surface of this ancient protoplanet will come into focus. Craters will reveal their walls and floors. Minerals will declare their identities. The shape and depth of the great impact basins will tell the story of the collisions that nearly destroyed it. And somewhere in the data, in the spectra, and the gravity maps, and the high-resolution images, will be the answers we have been seeking for 2 centuries. The cameras will see what no telescope has ever shown us, the texture of the craters, whether their floors are smooth with ponded debris or rough with exposed bedrock. The spectrometers will map the surface mineral by mineral, identifying exactly which clays, which serpentines, which organic compounds cover this ancient protoplanet. The gravity instruments will feel the subtle variations in Pallas's pull as the spacecraft orbits, building a 3-dimensional model of the interior that will finally reveal whether there is an iron core hiding beneath 4.6 billion years of accumulated regolith. And if the mission includes a surface element, a lander, or even a sample return capsule, then for the first time, material from the most critical boundary in the protoplanetary disk will be held in human hands, analysed in laboratories with instruments orders of magnitude more sensitive than anything that can be carried on a spacecraft. Until that day, Pallas orbits on, tilted, battered, silent, carrying its secrets through the cold, dark space between Mars and Jupiter, waiting with a patience that only a 4.5 billion-year-old world can possess. It does not know that we are watching. It does not know that we care. It does not know that somewhere on a small, warm, water-covered planet, less than 400 million kilometers away, creatures have built instruments capable of detecting the faint light that bounces off its ancient surface, and have spent 2 centuries trying to understand what it means. But we know, and knowing is enough to keep looking. We are a species that measures its own age in decades and its planet's age in billions of years. We have existed for the barest instant of cosmic time, a flash of consciousness on the surface of a world that has been orbiting its star for 4.5 billion years before we arrived. And yet, in that instant, in the few centuries since we first pointed telescopes at the sky, we have managed to detect a dark, distant protoplanet, calculate its orbit, measure its mass, determine the minerals on its surface, and begin to understand its place in the grand story of how the solar system was built. That is not insignificant. That is extraordinary. There is an asteroid between Mars and Jupiter. It is 512 kilometers wide. Its surface is darker than asphalt. Its orbit is tilted at an angle that should not be possible. It has been bombarded for 4.5 billion years, and it has not broken. It formed at the boundary between rock and ice, at the moment when the solar system was deciding what kind of worlds it would build, and it holds within its ancient body the answers to questions about our own origin that we have not yet been able to ask in person. Its name is Pallas, and one day we will go there.